Hi, it's time for another math easy solution, and today I'm going to go over vector functions and space curves. So this is a new chapter in my calculus book, and yeah, it's going to go over the first section of it. So it's going to be quite extensive. So if you don't have time to watch this whole video, you could play this video at a faster speed. Top secret life hack: your brain gets used to faster speed. And also here's a tutorial I made on it. And also you could download and read the notes, or read the notes on the Hive blockchain, or you could watch the video in parts, and timestamps of all the parts are in the description, as well as the links to the article and notes. And I'll also go over the video sections after I upload this, and then split them up into smaller bits. Anyways, so and also, yeah, you could skip through everything, including this intro. So anyways, let's continue further. So calculus book reference. Note that I mainly follow along the book Calculus Early Transcendental 7th edition by James Stewart, and I put a link to the PDF there. And I also use the following solution manual for this chapter, and there's a link there. And note, in some earlier videos, I used the 6th edition. Alright, let's continue further. So, calculus book chapter, and also what I started doing is put basically a link to all the notes and the playlist of the sections playlist. So the Hive notes and sections playlist for each chapter, or for each video of this chapter, are listed below. Vector functions. Yeah, this is going to be the full chapter, and this is the first video, vector functions and space curves. There's a link to the notes, and then this is going to be the link to the playlist. And let's continue further, and then afterwards we're going to go over all these and so on. And also, these links are also on MES links on the website, on the webpage, mes.fm/links. Alright, let's go over further. So topics to cover. So note that the timestamps will be included in the video description for each topic listed below, and I'll put these in the description once I finish this video. So vector functions, space curves, example 1, definition 1, example 2, space curves, example 3, plane curves, example 4, DNA helix, we'll go over example 5, example 6, using computers to draw space curves, then go over example 7, twisted cubic, and then go over charged particle moving in an electromagnetic field, then go over the exercises. Exercise 1 is on the precise definition of a vector function limit, and then recap on real valued function limits, and then go over solution 1 of it, and then an alternative solution 2, and also visualizing the definition. And then exercise 2 will go over properties of vector function limits, and then exercise 3 is a trefoil knot, and then exercise 4 is the trochoid. This is actually from an earlier video. I didn't have a chance to do that one, so I'll do that in this video. Anyways, yeah, let's jump right in. So, vector functions. The functions that we have been using so far have been real valued functions. Basically, just plug in a number inside and get some other one. We now study functions whose values are vectors. So then, yeah, basically you have a function that the inputs and or outputs are vectors. So because such functions are needed to describe curves and surfaces in space, we will also use vector-valued functions to describe the motion of objects through space. In particular, we will use them to derive Kepler's laws of planetary motion, and I'll do that in a later video. Again, this is just introduction to the chapter. So there's several sections on it, and this is just diving into what I'll be going over throughout this video series. So Kepler's first law says that the planets revolve around the sun in elliptical orbits, or in ellipses. So there's the sun right there. This one's actually Neptune. I think it's not showing Mercury. Mercury should be a closer one. There's Earth. This one is Mars. There is Jupiter. There's Saturn. This one is, I believe, yeah, this one is Uranus. And this is Neptune. And then there's Pluto all the way in the back there. All right, let's continue further. So in a later video, we will see how the material of this chapter is used in one of the most or in one of the great achievements of calculus, proving Kepler's laws of planetary motion, and so on. All right, so let's go over the first section of this chapter of the calculus books. So vector functions and space curves. So in general, a function is a rule that assigns to each element in the domain of an element in the range. And basically what this means is, and think about domains, usually just the x-axis. So if you have let's say this is the domain, the x, this is domain, and this is the range. That's pretty much all a function is. So let's say you pick any number in here, you just assign it another number over here. That's it. That's all it is. And then this one right here, here's another one, you just assign it over there. Yeah, and then what ends up happening is, well, yeah, so this is right here. And then the intersection is just where, or when you draw it out like this, that's just a point on the graph. So this is going to be another point. Again, that's just all it is. But basically, you take, and then if you plot this, so plotting the graph of function just means plotting this where each range and domain. So the x and y. Yeah, typically x is typically y. Anyways, let's put that there for just clarification. And now we go over a vector valued function. So a vector valued function or vector function is simply a function whose domain is a set of real numbers and whose range is a set of vectors. Yeah, so in other words, the domain in this case, we're going to have, I'll do it like this. This is a domain. Again, it's a set of real numbers, and it's typically, in this case, t, like a parameter. So if we have something like this, this will go over to the range, but it's a vector now. It's not just any number. This is going to be vector. So it could be multiple different functions in here, and this one, you can't really draw it out that well, so I'm just going to go just going to draw this like this. Yeah, this is just going to be, because you can have a bunch of different vectors. For example, this one right here, G like that, R, etc. And this goes into it, and then depends on what it is. And I'll put in here T. So you plug in the T inside here, and these could be different ones: 2-dimensional, 3-dimensional, and here's another one. Put in there, etc. So it's going to be it's more complicated than just this one here, and it's typically this one you can graph it out because it's just a simple line like that. So we are most interested in vector functions R whose values are 3-dimensional vectors. This means that for every number t in the domain R, there is a unique vector in V3. Yeah, this is in V3 denoted by R of t, or this is R vector of t, and this is V3 is basically 3-dimensional space there. You know, this is just basically a set of all points in 3D. So if the function f of t, g of t, and h of t are the components of the vector r of t, then f, g, and h are real valued functions called the component functions of R. And we write, basically, these are real functions plugged inside a vector, and then each one is determined by a parameter. Yeah, so what I'm going to write now is how you write this out. So if we have a vector like this vector function, this is going to be equals to this, and we're not drawing this in 3D, or writing this in 3D. So it's going to have x, y, z, or I, j, k components. So f of t, so as a vector form, and this is a function as opposed to a real number. And then this is going to be h of t, like that. And this also equals to, you could also write it in this I, j, k format. F of I vector plus g of t j vector plus h of t k vector, like that. Alright, and we use the letter t to denote the independent variable because it represents time in most applications of vector functions. Alright, so let's take a look at an example. So example 1, and this is just going over the domain of vector functions. So let's just say we have, if we had a vector function r vector of t, and it's a 3-dimensional one, and the components are t cubed, and then we have ln, it's going to be ln, and now 3 minus t, and this is square root t, like that. So, yeah, then the component functions are, well, this is just going to be f, g, and t. So we'll have f of t is going to equal to the t cubed. Let's write this a bit neater, t cubed. And then what we'll have, the next one is g of t is equal to ln 3 minus t, or natural log 3 minus t. And then h of t is equal to square root t. Alright, by our usual convention, the domain of R consists of all values of t for which the expression of R, if for R of t, the vector R of t is defined. In this case, ln, this one is not defined when this is negative inside there. So f of t, this one t cubed, this is defined for all t. This one's defined t needs to be greater than or equal to 0. Yeah, so I'll just read this out, and I'll graph this out just to illustrate it. So the expressions t cubed, ln 3 minus t, and the square root t, or t to the power of 1/2, are all defined when 3 minus t is greater than 0, and t is greater than or equal to 0 for this one. Therefore, the domain of R is the interval, and this is closed bracket. So the closed bracket means it can include 0. And yeah, it goes from 0 to 3, and this open bracket, just regular like that, means that it's excluding when this is equal to 3. So this is not when t equals to 3. It needs to be less than it, but it can equal 0. Because you can see right here, 3 minus t, you move this t to the other side, so t is going to be has to be less than 3 there. And I'll just put a recall right here. So recall, when we're dealing with t cubed, well, that's just that is defined for everything. So that just goes like this. This is just goes up like that and down like that. This is t cubed, and I'll say t, and this is put a y like that, and that's defined for everything. It just it goes to positive and negative infinity for t. For the other one, ln, recall that ln. It's going to look something like this. This is going to be, I'll put this as 3 minus t. This is how the graph of ln looks like. This is ln right here. Like that. And this part right here, yeah, this one is, that is just, yeah, this is when this part is 1. So in other words, t is going to be 2. So 3 minus t equals 1. Move this over, that's just 1 t equals 2. But anyways, it looks like that. Just and also recall, just because it's been a while since I did a math video. This is just means, yeah, this just means e to the y equals to 3 minus t. Like that. So then take the ln of it. That's just what it means. Yeah, so the y is, so basically take the ln. So ln of 3 minus t equals to e. I mean, e to the y, yeah, this equals to the y. So y just equals that. Yeah, here, I just fixed that up. So y equals ln 3 minus t like that. And this equals to log base e 3 minus t. Like that. And then also by definition here, when you have a number to the power of anything, it can't be negative. So this is always going to be, this always has to be greater than 0. Like that. So hence, that is sorted. And then the last one is just the square root 2. This is, I'll do it like this. This is just going to be, this is like that. I'll just put t. So square root 2 looks like that. And this is y like that. And yeah, so this can equal to it as well. It just, you can't have negative. You can't have a square root negative number. That's going to be on the imaginary side. So yeah, this is going to be greater than 0. This is. Alright, anyways, so hence this is, so yeah, hence the domain is this one here. And this one here, you could shift this over. So this is 3 minus t is greater than 0. So we'll have t is greater or less than, move this over, less than 3. And in this case right here, t is greater than 0. Greater than or equal to 0. And this one is t is infinity. T is element of all real numbers in this case. Alright, anyways, so just sorted that out. Alright, so that was just a quick example just to get our feet wet there. Yeah, I didn't even write this, and I thought it was straightforward until I just solved it. I'm like, might as well just explain this a bit more. Anyways, so now let's take a look at the limit of a vector function. So the limit of a vector function, R, is defined by taking the limits of its component functions as follows. Alright, and now this is going to be, we're going to call this definition 1, and we'll reference this many times. And basically this says right here, this definition, if R sub t is equal to, and if it's in a 3D, so we have these real valued function components, so f of t, g of t, h of t, like this, then, so if we have this, if, then limit, right here, limit as t approaches a of this vector function r of t is equal to the limit of every single component. So limit, this is by definition. So limit of t approaches a of f of t, limit as t approaches a of g of t, and limit as t approaches a of h of t, like that. And I'll just close this off like that. And yeah, this definition is provided the limits of the component functions exist. So all these exist, and then you put them together, you get the limit of the full vector function. Alright, going further, so note if the limit as t approaches a of the vector function r of t is equal to the vector L, this definition is equivalent to saying that the length and direction of the vector r of t approaches Or actually, this is plural, yeah. So length and direction of the vector approach the length and direction of the vector L. Yeah, so basically, yeah, the size of it, the length of it, and the direction where it's pointing, it's getting closer and closer to L. So equivalently, we could have used an epsilon delta definition. See exercise 1. This is the precise definition of the limit. I will go over that. And here, I'll quickly try to visualize this. I'm trying to do this off the top of my head. So if we have, this is going to be in 3D. This is going to be a Y, Z, and X. So let's say we had an L. That's like this. Yeah, that's our L vector. Well, actually, technically, this wouldn't be a vector. This would be just a, let's say this is the line L. And then let's say it's something like this. And then there's a point right here. And then this point right here is L. This is the L vector at that point, because this defines the whole thing. And then our other vector is it's approaching closer and closer to it as t gets closer. So let's say we have a vector like this, a different color. And here I'm just doing it off the top of my head. So let's say we have a vector like this. This is r of t vector, and then it gets closer and closer to this right here. It becomes pretty much on this. As it's basically getting closer and closer. And I'll just put it like this. This is r of t as t approaches a. So as t is approaching a, it's going to get closer and closer until it becomes basically flat with this. Like that. Just guys, leave it like that. Alright, yeah, going further. So limits of vector functions obey the same rules as limits of real valued functions. And yeah, basically, see exercise 2. We'll go over the properties of vector functions. Anyways, limits of vector functions. Anyways, continue further. So example 2. This one states, find the limit as t approaches 0 of r of t, where r is a vector, where this vector function is equal to, has components 1 plus t cubed times I vector plus t times e to the power of negative t j vector plus sine of t divided by t of, this is times by the k vector. Like that. That's the ijk. It's just x, y, z component. So solution according to definition 1. So we just apply the definition 1 right here. So we want to know the limit right here, and this is r of t. Like that. Yeah, so to take the limit, we just take the limit of each component part. So according to definition 1, the limit of r is the vector whose components are the limits of the component functions of r. Yes, we gotta just apply this. So what I'll do is limit as t approaches 0 of r sub t, or r of t, is equal to the limit, and I'll put this in a closed bracket. So limit t approaches 0 of, this is going to be 1 plus t cubed, and this is the I vector, plus limit t approaches 0 of t e sub t j vector, and then the last one, plus limit as t approaches 0 of sine t over t k vector. Like that. Alright, here I just made those a bit smaller to fit this in right here. So now what we could do is this equals to, well, just before we get to that, let's just look at, if we plug in 0 inside all of these, we get, we'll do that separately right here. So this equals to limit t, just plug in 0, just becomes just 1 plus 0. That just becomes 1. Like that. This is going to be, I'll just put it complete as 1 plus 0. I plus, now the next one right here, plug in 0. Well, what we get in this scenario, we get a 0. This is e to the negative 0. That's the same thing as writing, yeah, that's just going to be same thing as writing divided by e to the 0. That's just equals to 1 here by definition. 0 to 1, this just equals 0. Yeah, so then this is just gonna, I'll move this all the way to the bottom. And what I'll do is instead of that, this part right here, this is just 1 plus 0. So I'll just put this as 0. Yeah, this is 1. So I'll put this as I, like that. So that's I. This one is this vanishes. This is going to be equal to 0, J. And now the next one right here, this is going to be a sine. When you plug in the sine of 0, 0 divided by 0 is 0. So this is 0 over 0. And this one here, we need to apply the L'Hopital's rule. So I'll put an H like this for the L'Hopital's rule. So this can be plus, and basically it's undefined. So this is undefined. I'll put it like this. Yeah, 0 over 0, undefined. And the whole idea of L'Hopital's rule, yeah, it's basically we take the derivative, and then the whole idea of L'Hopital's rule is to see which one is going to 0 faster. Is it the top one going to 0? If the top one's going to 0 faster, then it's just going to be 0. But if the bottom is, then it's going to go to infinity or a different number. If they're going both similar, if they're going both very, very similar, they could cancel out too. So that's an interesting possibility. So anyways, so limit, this is going to put this in a bracket or like this. This is going to be equals limit t approach 0 and take the derivative of that. This is just going to be d over dt sine t divided by d over t of the bottom. And if we recall the sine rules, this is going to be the derivative of sine is equal to it just equals to limit approach 0. This is going to be equals to cosine. The limit derivative of sine is just cosine. T, then derivative of t is just 1. Plug in 0 for cosine, that's equals to 1. And this is k, and this is equals to, well, this becomes a 1 over 1, so equals 1. So in other words, we get equals I plus k. Yeah, the j vanishes, or you could also write it in a component like this format. This becomes just 1, 0, 1. So the vector is this. The limit as r as t approaches 0 is this vector right here, 1, 0, 1. And now here's just a quick recap on L'Hopital's rule from my earlier video. So L'Hopital's rule: suppose f and g are differentiable, and g prime of x, the derivative of the g is not equal to 0 on an open interval I that contains a, except possibly at a. Suppose that limit as x approaches as x approaches a of fx equals 0, and limit as x approaches a of g of x equals 0, or you could have it going to plus or minus infinity, or the f going plus or minus infinity, or the g going plus or minus infinity. In other words, we have an indeterminate form of the type 0 over 0 or negative or infinity over infinity. Then the limit as x approaches a of fx divided by g of x equals to the derivative. So basically, if it's continuous, and you had an indefinite form of 0 over 0 or infinity over infinity, we could just take the derivative. If the limit on the right side exists, or is if then this right here, it equals to this if the limit on the right exists or is infinity or negative infinity. So basically you can get to infinity, negative infinity, or exist. Or if you have another indefinite form, you can do it again. Alright, now let's take a look at the next section that's on space curves. So a vector function r is continuous at a if we basically have the limit is equal to each other. So the limit as t approaches a of r vector of t is equal to r vector at a. Basically when this is continuous at a if the limit exists. Yeah, I think that's more appropriate. Because I honestly thought it was a vector, but basically it's continuous at a if the limit exists. Again, very similar to just normal functions. Alright, so in view of definition 1, we see that r is continuous at a if and only if its component functions f, g, and h are continuous at a. So in other words, if it's continuous, if you go definition 1, so if r is continuous at a, then basically all of these limits have to exist, and they all have to equal, they all have to exist. In other words, they all have to be continuous. So they're all going to be have a real number value there. So yes, so the components are as well. there is a close connection between continuous vector functions and space curves. So suppose that f, g, and h are continuous real-valued functions on an interval I. Now, then the set of all points x, y, z in space where, so if we have basically now we're taking the vector function and basically drawing it in real 3D space. So the x1 is going to be now the x component is going to equal to the I component. So f of t. The y is equal to g of t. And now the z is equal to h of t. So now the actual coordinates in space have are the components of the vector function r. Yeah, and back to this statement. So basically, then the set of all points x, y, z in space where we have these x, y, z equals to the components of the vector, and t varies through the interval I. This is called a space curve, just a curve in space. So the equations above are called parametric equations of C. This is a set. This is a set of all numbers in space where it fits these functions, and t is called the parameter. We can think of C as being traced out by a moving particle whose position at time t is f of t, g of t, and h of t. And if we now consider the vector function r of t is equal to f of t, it has components f of t, g of t, h of t, then r of t is the position vector of the point P, point P is the position vector of it, and the point P is just anywhere on that set, on that space curve. So f of t, g of t, h of t on C. Yeah, so thus any continuous vector function r defines a space curve C that is traced out by the tip of a moving vector r of t as shown in the figure below. So what I mean by that is, let's say we have, this is our xy, this is our y. This is going to be, I'll make this even bigger. So this is our y, this is our z, and this is our x component in space, like that. And now let's say we have a space curve. So we have like this, and it goes like that. It loops underneath, and it goes all the way across like that. Let's erase this part like this. It goes like that. So it goes underneath and loops. And it goes like this, goes up. This is our C. This is a set of all points in the space curve. It loops like that. I'm just drawing it from my calculus book. And it loops like this. It loops around, goes under. Goes like this. And now this point right here is P. So let's say that's just any point P. And this one right here is P. And let's say the point P has coordinates f of t, g of t, h of t. Because it's a parameter, so it can loop around depending on what the value is of function. So it looks like that. And then r is going to be the position vector. It is a curve that C is traced out by the tip of a moving vector. So that moving vector is a position vector that goes all the way to this point P on it. So this is r of t. This is r of t, and this is in vector components, and now we do the triangle brackets. So that's a point, this is a vector. This is direction, length of it. And the magnitude or length is the distance to the point. Like that. So there it is. And this is going to be r of t. This is going to equal to, the same thing, f of t, g of t. But now it has a square bracket. The triangle brackets because it is a vector. The other one's a point. Vector, point. All right, there it is. Epic stuff. And just put this note right here. C is traced out by the tip of a moving position vector r of t. So that as this moves around, it's going to change and alternate and so on. It's going to be smaller here, bigger, and so on. And then if you just trace the tip of it, that's the curve C. It's just epic stuff. And now let's take a look at example 3. All right, this one states, describe the curve defined by the vector function r of t is equal to 1. This has components 1 plus t, 2 plus 5t. And this one, the k1 is a negative 1 plus 6t. Alright, so the solution, so basically the corresponding parametric equations are, so let's write down, I guess we want to describe this in vector 1, so we could do, this is going to be the f of t, g of t, h of t, or we'll just write it as our x component, because we're going to draw this in 3D space. This is going to be our x, 1 plus, this is the x component is just going to be x is equals to 1 plus t. Write this a bit neater. And then the next one is y is equal to 2 plus t. And then the z is equal to -1 plus 6t. And now these parametric equations which we recognize from my earlier video as parametric equations of a line, is linked to my earlier video. Basically parametric equations of a line passing through the point 1, 2, -1. You get the 1 from here, 1, 2, -1, and parallel to the vector 1, 5, 6, and that's going to be the direction of the constant in front of the t. So, and this one is 1, 5, 6. And again, just recall from my earlier video, here's the thumbnail of the sections of it. So parametric equations of a line. So if you have a line L, then you have R, you have the position vector, or the R naught is this point on it. And then this one right here, this is the direction vector. That's the A component, and that's parallel to this one right here. This is our V. Yeah, so A is parallel to this one. So yeah, this is going to be R is equal to, R naught plus A vector, which is parallel to this one, the same thing as just writing R naught plus T times V. Because this is parallel to it, but this is longer. So then you times it by a parameter T like that. I'm just refreshing my own sake. So this is going to be the point on this X, Y, Z on the point P. And now what we end up having is, yes, we have this component is X naught plus, X naught, Y naught, Z naught, plus T times it by A, B, C. And again, that's just the directions. This is parallel to this one right here. To get the same length, you just have to multiply it by parameter T. And what I mean by the same length is, this just changes. As you change this, you're going to have this one changing. So it's going to go all the way across, or smaller or bigger, depending on what the value is. So in other words, it's a point on it. So if you have a really big T, positive, it goes all the way. So your point P is going to go over there. Your R is going to shift all the way there. So again, it's just these are just parametric equations of a line. And again, that point on it, this one is through the point. This one's just the this X naught, Y naught, and Z naught. So that's going to be our 1, 2, and -1. In this case, it's going to be our X naught, Y naught, and the other one is the A, B, C. So A is 1, B is 5, C is 6. Yeah, so there is that one. There's the components, and split them up inside here because you can add these up. Anyways, so alternatively, we could observe that the function can be written as R equals to R naught plus TV. So again, that's exactly what it is. Yeah, where basically R naught is equal to 1, 2, -1, and V is equals 1, 5, 6. And this is a vector equation of a line that's given by the above image and my earlier video. There's your earlier video on it. And again, it's just they're all the same thing. You could write it as parametric equations like this. So you could write these as parametric equations like that, or you could just split this up into its component, a vector equation of a line. So R equals R naught plus T times V, where, when you have T times V, this one just equals to, well, TV, whatever parameter it is at that point. So anyways, that's all that is. Alright, now let's take a look at plane curves. So plane curves can also be represented in vector notation. Basically, it's like a plane. I think that's all it means. It's like an actual full shape like that. This one's in 2D. And so even if it's 2D, you can still graph it as vector notation. So for instance, the curve given by the parametric equations X equals T squared minus 2T and Y equals T plus 1. So this is in 2D. See my earlier video, and here's screenshots from my the calculus book notes on it. So this is from an earlier video, can also be described as the vector equation. So here's just this just recall my earlier video first. This is X equals T squared minus 2T, and then Y equals T plus 1. If you graph it out, it looks like this, and goes from here. It goes from here all the way up like that. Just a horizontal parabola there. Yeah, but now we're going to write this in vector notation. So what we're going to get is, well, R of T. This equals to, well, now just write these in components. So the first one is the X one. There's T squared minus 2T. Minus 2T, and then the next one, this one is 1 plus, or T plus 1, like that. And this is the same thing as just writing it as in 2D. So this is going to be 2T, T squared minus 2T. This is going to be I plus, and then this is going to be T plus 1 plus 1 j, like that. And in this case here, because we're dealing with 2D, this is where I is equal to, this is just going to be the standard basis vector 1, 0. It just follows along the x axis, and then j vector is equal to 0, 1. Like that. And here's just a quick recap from my earlier video, or recall from my earlier video, that I, j, and k are standard basis vectors in 3D, but if you just have I and j, that's just in 2D. So what we'll have is standard basis vectors, here's 3D, and the whole idea is if you have a vector a right here, you could just multiply it by the standard basis vectors, just any constant a1, a2, a3, times it by this one here is going to be 1, 0, 0, j is 0, 1, 0, and then k is 0, 0, 1. So just multiply it by those like that. Anyways, and in 2D, you just remove the k variable, or the k vector. Anyways, let's take a look at example 4. And this one asks, sketch the curve whose vector equation is r of t equals to cosine t times I plus sine t times j plus t times k. So let's take the k vectors. So let's take a look at the solution. So the parametric equations for this curve are, so we're just going to write x equals to cosine of t, then y is going to equal to sine of t, and like this, then and then z is equal to t, like that. Alright, but one thing to notice is that since we have this x and then y are just cosine and sine, well, since we know that, well, x squared plus y squared, this just equals to, if we just square those, this just equals to cosine squared t plus sine squared t. And this is just the Pythagorean identity, or this Pythagorean identity. This just equals to 1. Yeah, and what this means is, well, then the curve must lie on the circular cylinder x squared plus y squared equals 1, and it's a cylinder because basically t is any value. So I mean, z is any value t, and that just goes up. That's just the vertical axis. So you draw a circle and it goes all the way up and down. So the point x, y, z lies directly above the point x, y, and 0. So in other words, just above it. So it's the vertical cylinder, which moves counterclockwise around the circle x squared plus y squared equals 1. And that's because as when you plug in 0 right here, cosine squared 0 plus sine squared 0, this just becomes 0. And then as you increase it, this is going to be positive. So in other words, when you increase from the x and y, and it depends on which how you have the axis aligned. If you have x and y like this, it's going to go counterclockwise. So going further, so which moves counterclockwise around the circle x squared plus y squared equals 1 in the xy plane. The projection of the curve onto the xy plane is a vector equation r of t. Move some room right here actually, like this. Has r of t, let's leave it like that. And I just see my earlier video on this. So the projection of the curve on the xy plane is vector equation r of t cosine, equals to cosine t sine t, like that. And basically, I'll move it like this. This is the projection of that equals to this right there. And you can see my earlier video on this. And again, I went over this earlier in my earlier video. When you just have cosine t. So if you have a point right here, let's draw this right. This is a point right here. This is our x. And that's our x, this is our y. In other words, this is just our cosine and t. And then if you square those, that's just a circle there. So you just have a circle like that. So anyways, long story short, that's just a circle from my earlier video. Because x is cosine t, sine t, this has to be, and then using Pythagorean identity equals to 1, the squared, so then it's just a circle. So since z is equal to t, the curve spirals upward around the cylinder as t increases. Yes, because this is a projection onto it. This is when t is equal to 0, or when z is equal to 0. So when you set z equals to 0, it's just flat on it. But then as your z is increasing, so for example, even though it's still going in a clockwise there on the projection, it's actually increasing more and more as z is increasing. So then the curve spirals upward around the cylinder as t increases. The curve shown in the figure below is called a helix. And so here I'll just graph how it looked like. So it's gonna have a cylinder shaped like this. Let's draw the cylinder first. So for now, first I'll do is draw this the z component, and it's gonna be now in a cylinder like that, and it's gonna go straight down like this. Draw this, finish off the cylinder like that, and this goes like this. This is the y, this is the z, and this is the x, like that. I'll draw this for completeness all the way down. Actually, yeah, let's draw this first one, I guess. So this is at the point 1, 0, 0, and I think that's where it starts off at. Yeah, it starts off at here, because if you plug in 0 inside here, 0, cosine t is going to be 1, sine is going to be 0, this one is 0. So it starts off here, and then it's going to go around in a circle, counterclockwise. So there's the y is going to go counterclockwise like this. And at this point right here, this is, it's going to be on this point right here. This is 1 there. So it's going to be 0. Now x is 0, y is 1. And now the question is, what is what is z? And if you look at right here, so this goes from here all the way to, this is at 0, 1. So in other words, it goes, t is pi over 2. Yeah, then that's a full 90 degrees. So that is t is equal to 90 degrees. Yeah, pi over 2. Or 90 degrees. And again, we already written this down there. So that's already done it from my earlier video. And so in other words, this is going to be pi over 2. That's our z. In other words, that's the height here. That's the height is pi over 2. Like that, yeah. And then it's going to continue on. It's going to circle around like this. I should make it a better circle. Like that. I should make it really light. Like this. It goes around. And then it circles back in dark. Like this. Whoops. And then circles back in light like that. And I'll make it dark like this. And so on, like that. Yeah, so it just goes, circles around like that. And I'll draw this for completeness, all the way down, dot, 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 and all the way across like that. And there's our y like that. So that's how it looks like. Yeah, it's pretty good actually. I was surprised myself. And yeah, here's a better illustration from my calculus book, which is again I just copied. There's the there's a cylinder. Starts off at 1, 0, 0, and it curls around. But basically, it's curling around in a circle, counterclockwise circle, but it's also going upwards because of the z parameter or the t, and that increases this pi over 2, and so on, goes up and up and up and up. Like that. And also here what I've done is I've graphed it on GeoGebra's 3D graphing calculator. There's a link to it. And there's a cylinder x squared plus y squared equals to 1. That's just to graph the cylinder. And now you can graph it as a curve. So this cylinder right here, if you just put it like here, it assumes the t values are, the z value is infinite. So it just draws a full cylinder, and you can see it wrap completely around it. And this is the curve, cosine t, sine t, and t. And I made it just up to 6 pi, so 3 revolutions. And so on, looks like that. So pretty fascinating stuff. I'm going to go, here's the link to it. And you can hide it. There's a cylinder. There's a curve. And you could play around with it and so on. Yeah, it's pretty epic stuff there. Zoom in and zoom out. And there's the top. Yes, top is a perfect circle. And again, just goes up because of the Z parameter. So fascinating stuff. And here now, let's take a quick look at the DNA helix. So the corkscrew shape in example 4, this one right here, just corkscrews around like that. Yeah, this is familiar. It's familiar from its occurrence in coiled springs, and it also occurs in a model of DNA or deoxyribonucleic acid, the genetic material of living cells. In 1953, James Watson and Francis Crick showed that the structure of the DNA molecule is that of 2 linked parallel helixes that are intertwined as in the figure below. So it's similar to that shape here, but now there's 2 and they're intertwined with these base pairs inside like that. So it's a double helix. And here's more info. So here is more info on DNA and RNA from my earlier videos, and here's links to them. And I just put the screenshots that I made because they're pretty epic screenshots. Yeah, so DNA is contained in the nucleus of every cell of the body, or at least most of them, and so on. I'm not sure the specifics, but anyways, so this is generally the case. So here's RNA is basically is a single strand typically. This is typically double strand DNA, and then these are the base pairs right here, or these are these are the base pairs that that line up. Or the these are nucleobases, and they line up with each other. Here you have cytosine. So for RNA, you have the CGAU, so cytosine, guanine, adenine, and a uracil. And this one's the same thing. You have cytosine, guanine, and an adenine, except uracil, you have thymine for DNA. And then there's the corresponding match right here. This is the red one matches with the yellow. Red, yellow, and so on. And then this one here, yeah, these are base pairs. So helix of sugar phosphates, and so on. And here is there's a cell. So if you have an animal, it has a bunch of cells, and each cell, if you zoom into each cell, you go to get the nucleus, and inside there you have the chromosome, and inside the chromosome you have basically a giant spiral of DNA like that, and it's like that. So it's pretty fascinating stuff there. So that's like the genetic code. And here's another diagram. This is a central dogma of, here, I'll just fix that up. So central dogma of molecular biology states that the information flows from DNA to and from RNA to protein, and never from protein. So you can get one DNA to another, then you can go to RNA. So you can go from here to here, and you can go backwards in some cases, like reverse transcriptase enzyme and so on. But typically it goes from DNA to RNA. So our DNA creates RNA, and then RNA creates the protein, and it never goes reverse. So biology states that the essential dogma of molecular biology states that information flows from DNA to from RNA to protein, and never from protein. So it does not go from here to the reverse. And here is a more detailed diagram of the molecules and the base pairs and so on. So here's pyrimidines are on this side, purines on this side, AG, there's TC, and so on. That is different phrasing for them, and they line up with hydrogen bonds like that. And there's some more info on this, how these are some, these are the exons. This is the RNA letter. It cuts off the RNA, go back here. So you have the DNA, and then it goes, we have a protein there, or this ribonuclear protein SNRP goes and basically duplicates from here. It creates an RNA. First creates like this, then you have other ones cut off. The introns are the cut off ones, and the exon is what's left over, and that's the mature RNA only exon. So it cuts off all the excess and other bits of it and so on. Anyways, you get this generally like that, a mature RNA from this DNA. And so on. Yeah, so that's the mainstream biology. So let's continue further. And now let's take a look at example 5. Example 5 states, find a vector equation and parametric equations for the line segment that joins the point P1, or here I just moved it over just so it's in one line. So that joins P, the point P, which has coordinates 1, 3, -2, to the point Q, which has coordinates 2, -1, and 3. All right, so that's what we have there. And here, it's quickly erased it just to add it as one sentence anyways. So it's pretty clear, pretty straightforward. So P, 1, 3, -2, and then to the point Q, 2, -1, and 3. So we want to find a vector equation and parametric equations for this line segments connecting basically 2 points P and Q. So connect them and find the equations and so on. Alright, so let's take a look at the solution. So in my earlier video is a link to it, and this is the thumbnail. So I tried to make thumbnails as detailed as possible, as basically self-encompassing as possible. So we found a vector equation for the line segment that joins the tip of the vector R0. So here is this R0. This is remember my earlier video equation of line segment. So it connects this. We can get this line segment by connecting R0 up to here. This is the tip of this line to the tip of the vector R1. So this is from if we consider this as P. This would be our Q. And actually, no, the Q is over in this case here. This is just the general. This is the general formula, and this is R1 right there. This could be a P. This could be Q, and this is separated. The full vector across is V, and then T times V would just be just a parameter times by the parallel vector v, like here. This would be your v, parallel to this times by t, and shift it over all the way across. Yeah, this would be actually a parameter t. Yeah, and yeah, this is just a parameter t actually. This is t times v. This is just a parameter multiplied by this to get it to just a general one. And then if you want to specifically to R1, this would just be t is equal to 1. Yeah, so in my earlier video, so I basically showed equation of a line segment. So it goes from R0 to R1, and then line segment is defined as this is the vector R of t and vector formation. Then we'll have a 1 minus t, R0 plus t R1. So this happens when you plug in t is equal to 1. What ends up happening is, well, this vanishes, and this goes to 1. All we're left with is R1. So all we're left with is this. So that is correct. And when you plug in t is equal to 0, this vanishes. This vanishes. All we're left with is 1 times R0. So in other words, all we're left is with here. So hence that we set up the segment such that everything vanishes outside of this, and everything vanishes outside. So all we have is this line segment. So yes, I knew it was just me scribbling a bunch just to recap on that. So in our case, the vector equation of the line segment from P to Q, so P is this, and there's Q, and that's going to be, well, what we're going to do is take, in our case, take R0 vector. This equals to, well, it's going to be the R0 in our case. This is just point P equals to point P. So this is going to be 1, 3, negative 2. And this is vector form. So 1, 3, negative 2. And we take R1 vector. This is, this R1 vector. I'll just fix this up. This equals 2, and this is just the vector from, this is the point Q, but as a vector form. So position vector of it. Because if you have a point, let's say Q like here, this is, the position vector would be R1. The position vector is actual vector. So this is a point, then the vector, you just need to make these brackets going from the origin. So 2, negative 1, and 3. So 2, negative 1, and 3, like that. Alright, so thus, our vector equation of the line segment is R of t equals 2, and this is going to equal to just 1 minus t times by R0 0, R sub 0, and then plus R, this is t times R vector 1. And again, this is for t is between 0 and 1. Less than 1, greater than, equal to 0. Yeah, so that is less than 1, greater than, equal to 0. So it's like that. And then we just plug in our values. This becomes 1 minus t. And then this is going to be a vector 1, 3, negative 2, plus t, 2, negative 1, 3, like that. Yeah, and then we could go, or we could just solve this even further, or put it there. Yeah, put it like this. Or, and then this equals 2. Just keep going, and then just simplify this also. Multiply this inside, and then basically sum these all up. Yeah, so what we could do is, well, 1 minus t times that inside. So we have this is going to be 1 minus t times 1 is just 1 minus t, and then plus 2 times t. So plus 2t, and then now the next segment, the y component, that's 1 minus t times 3. That's going to be 3 minus 3t. And then the next one is going to be, well, t times negative 1, negative t. And then they keep going further, so we go 1 minus t times by negative 2, so that's going to be negative 2 plus, the negative becomes positive, plus 2t, and then t times 3, that's going to be plus 3t, like that. So that is what you have. And I'll put the or around here, or. And then what we could get now is, now we just simplify this. This equals 2. This is going to be negative 1 and then plus 2t. That's just going to be, well, 1 plus t, like that. And then 3 minus, 3 is by itself. Then negative 3 minus t, that's going to be, well, we're going to have a 3 minus 4t. And then now we have a negative 2 by itself. And then plus 2t plus 3t, that's going to be 5t. And again, this is 4. And I'll just put this all in there. So thus we have r of t is equal to this for t is less than or equal to 1, greater than or equal to 0. So we could box this whole thing out. So there is our vector equation of a line segment. Alright, so that's a vector equation, but we're also asked parametric equations. Parametric equations, well, we just put x, y, and z for all of these components. So the the corresponding parametric equations are x equals 2, 1 plus t, and then the next one is going to be y is equal to 3 minus 4t, and then the next one is going to be, well, z is equal to negative 2 plus 5t, and again, we have t is less than or equal to 1, greater than or equal to 0. So that is our parametric equations. Alright, and let's graph this out. So the line segment PQ is graphed below. Well, it's going to be pretty straightforward. I'll just draw just draw it quickly, then we'll graph it with Desmos. So this is the y. Yeah, that's a y. This is our z. This is our x. Like here is going to be your x, like that. And now we take a look at the components. Yeah, so we'll just beginning points right here. This is 1, 3, negative 2, and then 2, negative 1, 3. So let's draw out 1, 3, negative 2. So it goes x once, 1, and then 3. It goes like this on the y. 1, 2, 3, and then it goes negative 2. So it goes all the way to the bottom. So this is going to be, I'll draw this down like this. I'll actually just draw it like this. And it goes 1, 2, so at the bottom. So it's going to go here, it's going to go across here, and then down. So it's going to look something like here. So this is our P. This is P. This is our 1, 3, negative 2. Like that. And then the next point is going to be our, the next point is going to be our Q. And our Q it goes all the way to 2, negative 1, and 3. So that goes 1, 2. And then this also goes to, negative 1. So it goes to negative 1. Let's go that again. So negative 1 and 3. So negative 1 goes backwards. So negative 1. And then 3 goes up 3. So in other words, 1, 2, 3. So it goes like this. And then this goes sideways like that. So this is going to go dot, 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 dot all the way across the top here and draw it and roughly 3D. It goes like this, dot, 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 and then all the way across like that. So it goes like this. This would be the point right there. So it would look something like this. This is our line segment, and it goes from here to there. So it's lining up with all that. So what I'm going to do is I'm going to change the color. I'm going to change the color quickly. And let's draw it in, let's go in red. So red. So I'm going to draw it like that. So in red. Goes straight across like that. Draw it a bit neater. Yeah, so this is our R. R segment. Yeah, so that is our R. And again, it goes from P to Q, so it goes from, put an arrow like that. So that is that. I'll draw this back to here, and then we'll draw it in GeoGebra. Alright, and now here's the graph in GeoGebra's 3D graphing calculator, so there's a link to it. And I put the point Q. Q is a 2, negative 1, 3, and then P is 1, 3, negative 2. And here is the just equation. I couldn't do, apparently the equation, this one just creates a full line, so it goes all the way across, past, and forward. So I don't know how to make that not a segment, but there is a segment here. You could just write PQ and it just automatically puts a segment. And also gives you the length 6.48. So I put that in, and then it goes across here. So I put the lines 1 plus t, negative, and this is 3 minus 4t in vector form. Then negative 2 and plus 5t. There should be a way to add a parameter, but anyways, that'll be for another day. So that is this part right here. So 1 plus t, 3 minus 4t, and a negative 2 plus 5. So let's go to the line segment. And again, it draws exactly where P and Q should be, and that's exactly where ours was. So here's P and Q. If I draw this like here, it goes a full line. I think there should be another parameter. I'll do that for another video if I do a line segment ever again. So there it is. And here's the segment. It matches up. So again, it confirms it's it. And there's the P, there's the Q, and so on. So you can move this around like that, and so on. And yes, fourth. And I'll remove that. And there should be a way to add settings. Add this point. So show label. Show value. Name and value. Okay, that would be cool. Yeah, and it shows you the numbers. This is 2, -1, and 3. So I want to do that for this as well. I do like that. Labels. Show labels and name and value. Alright, and I am going to alright, here just quickly pause it, took a screenshot there, so let's go back here and let's remove this one and add it with the screenshot. So there it is with the screenshot, with the numbers. There's Q, 2, -1, and 3, and then this one is 1, 3, -2. Yeah, so epic stuff here, matches exactly as our little graph there. Yes, anyways, that's epic stuff there. Alright, and now let's take a look at example 6, and this one states, find a vector that represents the curve of intersection of the cylinder x squared plus y squared equals 1, and the plane y plus z equals to 2. So this is a line, there's no square. This one is just a circle, and then the z is just infinite, just up and down. And basically you get a cylinder. So here, I've graphed it out. Here's the solution. So, solution, the figure below shows how the plane and the cylinder intersect. So I'm going to go to GeoGebra right here. Alright, so here's GeoGebra, and there's a cylinder, there's the plane, and then there's the intersection right there. So we want to find this points of intersection there. So basically find a vector function that represents all the points where this intersects the plane and this cylinder. Alright, so let's get back into here. So here's how it looks like, and so on. Alright, so the figure below shows the curve of intersection C, which is an ellipse, and you can see this is an ellipse right here. A circle would be a perfectly perpendicular to this. There's a horizontal plane cutting it through, but it's at an angle, so it's going to be an ellipse. And before I graph it, I'm going to find out all the points of intersection, or just several points. I'm going to find 4 points. And yeah, 4 points for just specific numbers that are easy to calculate. So what we have is we have the cylinder x squared plus y squared. Or is this x squared plus y squared? This equals to 1. Alright, and then we also have the plane y plus z equals to 2, like this. Alright, so let's just double check that. Yeah, so we have x squared plus y squared equals 1, and y plus z equals to 2. Alright, so what we could do here is I'm just going to rearrange this y to make it equal to 2 minus z. So this one is just equal to y, move the z over to the other side, 2 minus z. And then we could throw this inside. Yeah, so we could throw this inside there, and then we get basically the point of intersection. So we put the y inside there, replace it, and this is at the intersection. I'll put at intersection. At intersection. So at intersection, we're going to have the equation where these all have to match. So we're going to have x squared plus y. Well, y, if it's at the intersection, it needs to fit both equations, so we plug that y is going to equal to 2 minus z squared plus 1, like that. And whoops, not plus 1, this equals to 1. All right, so we have this, and now let's find a few points. So at so I'll move this arrow like here. So at an easy one, this would be at x equals to 0, so that just vanishes. At x equals to 0. What we end up having is, well, we're going to have a 0 is x squared plus 2 minus z squared equals to 1. In other words, now we could take a square root. So square root is just going to be, well, 2 minus z squared both sides equals to plus or minus square root 1. And that just equals to, well, because again, you can have a plus or minus, yeah, minus 1 times minus 1, it also gets equals to 1. So, and if we go further, this just equals to plus or minus 1. Now, I'll just write that down for completeness. So this equals to plus or minus 1. So in other words, what we get is, well, z, move this over to the other side, and then move this over to this other side. We're going to have z is equal to, well, 2. And then instead of plus minus, we get minus plus. Again, it doesn't matter. Minus plus 1. I just do it for completeness, just keep track of the direction of the arrows. But it doesn't matter because this is either or. So then, in other words, z is equal to 2 minus 1 is 1. Or 2 plus 1 is 3. So z is equal to 1 or 3. Alright, so we have that, and then we could plug that into y. So then this means that y is equal to, well, 2 minus z, which equals to 2 minus 1. I'll just do it like this. Equals 2, yeah, like this. Like that. Yeah, just fix that up. So make it like that equals to, well, 2 minus 1 or 2 minus 3. So this equals to 1, or we can have it as negative 1. Alright, so thus this means we have, well, 2 points of intersection. Thus, 2 points of intersection for this case. So we have at x is 0. So at x is 0, we're going to have z is equal to 1. And if z is equals to 1, y is equal to 1. Like that. Or, and then x is 0. And then if z is equal to 3, put a blank, we'll go 3. Then y is equal to negative 1. Like that. So we have 2 points there. And going further, so likewise, for x is equal to another, let's just pick another number, plus or minus 1. And here, the reason I put plus or minus 1 is because right here, we could put a plus 1 squared or minus 1 is just, it's still going to be 1, and it's a simple one to evaluate. So then what we end up having is, we're going to have, well, plus or minus 1 squared plus, this right here is at the intersection, 2 minus z squared equals to 1. Like that. So same thing as before. Now this one, plus or minus squared, is just always going to be equal to 1. Equals to 1. And move this over to the other side. This cancels, so what we end up having is, well, a 2 minus z squared. Again, I'll just put it for completeness, 1 minus 1, or I'll just cancel that. Yeah, this just equals 0. Like that. So if it's 0, square both sides, we're going to get a 2 minus z is equal to a plus or minus, well, square root of 0, it's all just going to be 0. And then so we solve for z, just move it over to the other side, so z is equal to 2. Well, yeah, so z is equal to 2. So this means, thus, well, actually, before we even get to that, we'll put the y. And the y is going to be y is equal to 2 minus z. So 2 minus z is equal to 2 minus 2 equals 0. Yeah, so thus what we have is, thus 2 more points. 2 more points. And these are of intersection, so we're going to have 1. So when we have, when x is 1, when x is 1, we're going to have z is 2 and y is 0. So it doesn't change anything. So it's always going to be 0 and 2. And likewise, yeah, 2 more points. This or, I'll put, or and. So instead of or, put and then the next one is going to be, well, when x is negative 1, it doesn't change the z or y values, so it's still going to be 0 and 2, like that. Alright, so now we have 4 points, and we're going to graph these out, and we're going to get the ellipse. These are the points of intersection, so let's just graph these out now. So this is going to be, I'll make it not so big. Okay, this is going to be our y. This is going to be our x. This is going to be our z. And now what we have is, let's just put some points here. So at, yeah, alright, let's do the first one. Let's just put this 1, 0, 2. So this point here at 1, so we go x1. And 0 is stays stationary, then we go up to 1, 2. So in other words, it becomes this part right here. So this is a point right here. This one is going to be our point 1, 0, 2, like that. And that's this one right here. Now the next point is going to be at negative 1. So we go backwards 1. Negative 1. Like here. Yeah, so that's negative 1. And then we go up 0. Doesn't... Oh, you know, that's the y. That's the y. Whoops. Yeah, so it goes like this. This is on this side, negative 1. And then we go up, we go to the right 0, and then go up twice. It's going to be 1, 2. So it's going to be another point right here. This is going to be at negative 1 and 0 and 2. Like that. So it's on the same plane. Draw this a bit nicer, like that, in 3D. Alright, that's that point. And now the next one is going to be at, right here, 0, 1, 1. So at 0, and then we go 1 here, and then 1 here on top. It's going to be somewhere around here. Alright, so that's going to be our 0, 1, 1. Yeah, I'll put this like this. This is our... Put the arrow like that. This is a 0, 1, 1. Alright, and it goes like this, and this is going to be a shape like this. This is be an ellipse. We'll draw it better later. But anyways, we have a point there, and then one more point, 0, -1, and 3. So it's 0, then it goes -1 over up here, -1, and then it goes 3 up top. So all the way here. So it's going to be somewhere around here. So again, try to visualize that in 3D. It looks something like that. It is a horrible drawing. But you get the idea, and it's going to be actually on points of this intersection across like that. Alright, so that's that. Alright, yeah, so that was a pretty bad drawing, but here's a better illustration from my calculus book. Alright, so here's a better illustration. There is the plane, there's the plane y plus z equals to 2. So basically a line like this, and the x direction goes infinite back and forth. That's pretty much, think of it as a line from in the x z plane, and then the in the zy plane, and then the x one goes to infinity. And this one here, x squared plus y squared equals 1, is just a circle with an infinite vertical component. The z goes to infinity, up and down. So that's that. And then if you see the plane of intersection goes to here, and there's the points 0, -1, 3, -1, 0, 2, 0, 1, 1, 1, 0, 2, and exactly what we had here in this one. I'm going to put stuff like here. This is going to be our -1, no, 0, -1, and then 3. Yeah, I think that's what we have. 0, 0, 1, and 0, -1, and 3. So 0, -1, and 3. And again, this is a bit smaller scale. This one is a better shape there. All right, and again, I include the screenshot from my calculus book as I understand my own limitations. There's a drawing. There's a better one. Anyways, the projection of C onto the XY plane is a circle is a circle x squared plus y squared equals 1, z equals 0. So now we're going to look at this projection right here. If we take this, the projection of C, so this is our C. This is our C. If you project it all the way straight down, what you end up having is actually a circle. You're going to have a circle like that. And that's just going to be the circle y squared, x squared plus y squared equals 1, and then z is equal to 0. So just set it to 0. So we know from my earlier video that we could write it like this. So if we have a circle, so it's just a circle. If this is the y, and this is the x, and then we also know this is also the x squared plus y squared equals 1. Y squared equals to 1. And this is because this equals to, for completeness, because this is a different example. So that's our x and y. We also know that x squared plus y squared equals to cosine squared t plus sine squared t equals to 1. And again, that's just a parameter. Yeah, this is the Pythagorean identity. So that means, and we also, basically means that we could write this in parametric equations using sine and cosine, and that's just an equation of a circle. And where when you have t equals to 0, plug into cosine of 0 is 1, sine of 0 is 0, so we have 1, 0 as a starting point. And then it loops all the way around in a circle. Like that. So that is what we have. And yeah, so we know from my earlier video that we can write, so we could basically write these in the components. We can write these as parametric equations. So we have this, so we can write this at the x component is just going to equal to cosine of t. The y is equal to the sine of t. Sine of t. And this is all for 0. T is between 0 and 2 pi, because it just goes, after that, it just follows back in the same circle. So from t is between 0 and 2 pi, we have a circle. We don't have to do loop that many times, just one time. So, because all we need to know is one loop. We're just asked to find the shape here for one intersection, not infinite in loops. All right. So from the equation of the plane, we know that the equation of the plane right here is just y plus z equals to 2. So we have y plus z equals to 2. Yeah. So then, for parametric equations in 3D, our z, rearrange that, is just going to equal to, move this 2 on the other side, move the z on the other side, and so on. We're going to get z is equal to, z is equal to y minus 2, and then replace, actually, and not z as y equals 2. We'll move the y on the other side, so we have positive z. So we're going to have a 2 minus y, and y is equal to sine t. So this equals to 2 minus sine t, like that. Yeah, and since we're asked to find the parametric equations of this, so right here, come back here. So find a vector that represents the curve of intersection. Yeah, it doesn't specifically say that find the parametric equation, but that's pretty much what we can do. So we could write parametric equations for C, the intersection curve, as right here. We could write this as x equals, now it's in full 3D. X equals to cosine t, y equals to sine t. So now we have a 2D circle. And now we're going to have a 3D slanted ellipse right here. It's going to be z is equal to 2 minus sine of t, where t is between 2 pi, or 360 degrees, and 0, like that. So that is our setup there. And now the corresponding vector equation is, we could write it in this format. So r of t, we could write this as, just write this in the basic. We could either write this as, I'm going to write this in both formats, so cosine t like that in the triangle brackets, sine t, and then 2 minus sine t, like that, or the other one is just the cosine, so the calculus book has it, cosine I plus sine t j, and then plus 2 minus sine t. Sine t, and then this is k, and this is again for all this is for 0 is less than or equal to t less than or equal to 2 pi. So that's the range. All right, and now this equation, or whichever one you want to use, this equation is called a parameterization of the curve C. All right, that's my pronunciation. The arrows in the earlier figures, I'm not sure if there's figures. I think it's just figure. Yeah, I didn't put the arrow over there. So in the earlier figure right here, see these arrows going down, and this going up like that, and so on. So it's going in a circle this way, counterclockwise. And yeah, those ones, the arrows in the earlier figure indicate the direction in which C is traced as a parameter t increases, and we could see that from ours. So, and this one goes up like that because, well, it's based on the parameter t, not the x. Because right now we have x is equal to 1, -1, there's a 0, so we don't know where it's starting from, but when we start from t, so let's go from t equals to 0, what we end up having is, we're going to get, so when you plug in t equals 0, we're going to get a cosine t is 1, and then sine of t is 0, and then 2 minus sine of t is 2, like that. Yeah, so that is that. So in other words, the starting point is this right here. So that's the starting point. And again, there's our x, and think of it as the this is the at 1 0 at the bottom there. So this is 1. So, and it goes around like that. So basically, think of it the angle goes like that from t is or the theta. So if you look at it as theta, yeah, t is in this case the angle, and starts at x equals to 1. And that's the same thing right here. So it starts off here. I'll just draw it anyways, like that. And this is our t. And actually, instead of that, I'll just do it like this. This is I'll just draw the full thing like that. So that's our t, like that. T goes around in a circle like that, and so on. So then this is the first point. So it starts off right here. Yeah, so that's the first point, and then the next one, and so on. And then the next one, we'll solve it right now. So the next one is, let's go at t equals 2 pi over 2. That's 90 degrees. So if you think about it this way, if you go at t equals pi over 2, that's at 0, 1. So this is at 0, 1. And that's because, well, when you plug this in, so at pi over 2, cosine of pi over 2, that becomes 0 now. That's just the cosine of 90 degrees. That's a 0. And then sine, that becomes at the maximum 1. And then 2 minus 1, that's just going to be 1. Yeah. So in other words, this is the next point. And then you obviously see, so it goes from here all the way down here, and it's going to go back up. And so that's set up there. And I'm just going to erase this as well. Or what I can do is, this is t. Like that. T goes from there. All right. Alright, so now let's take a look at the next section. That's on using computers to draw space curves. So space curves are inherently more difficult to draw by hand than plane curves. For an accurate representation, we need to use technology. And plane curves is pretty much like on the same plane. Like this one here is on the same plane. So that intersection right there is still on this plane. But now if you want to draw some advanced setups right here, we're going to need a computer. So we're going to need to use technologies. For instance, the figure below shows a computer-generated graph of the curve with parametric equations. X equals to 4 plus sine 20t, and then all of that times by cosine t, and then the y is equal to 4 plus sine 20t, then all of that times by sine t, and then the z is equal to cosine 20t. So you're gonna get a vortex right here, a toroidal spiral, or just a toroidal spiral vortex, etc. there. So that's an amazing shape there. So it's called a toroidal spiral. Yeah, because it lies on a torus. So it's on a torus and it spirals. Yeah. Another interesting curve is called the Trefoil knot, with equations right here. X equals to cosine, 2 plus cosine 1 plus 1.5t times by cosine t, all of that times by cosine t. And then y is equal to 2 plus cosine 1.5t, and then all of that times by sine t. And z is equal to sine of 1.5t. So it looks a crazy shape like this, a trefoil knot. So here are the graphs in GeoGebra, and so what you could do is just plug that in. You could write a curve right here. So curve, and then you can also indicate right here the parameter. So I put the x, y, and z components, put with the parameter t, and then you indicate how much the domain of t. So I put t is from 0 to 4 pi. This one's 0 to 2 pi. Again, I just do it until something lines up, until it does a full loop. So here it is, both of them graphed like that. So it's pretty amazing stuff here. So here's the full graph. You can hide them, and you can put that like that. Anyways, that's GeoGebra. So I'll move this away like that. So here's the shape. It's a pretty calculating intensive. And if you go upwards like that, look at that perfect perfect shape on top there. But then from an angle, it does not look like that. So look at that. It looks all out of whack. But now you can see this perfect triangle, three-sided shape, and then there's the sinusoidal waves going up and down, back and forth, but in a spiral. So amazing stuff. And there's the 3D. There's sideways. You can see them all different shapes and stuff. So again, all these links you can go and view them and so on. Absolutely amazing stuff here. Yeah, so that is quite amazing. So even with a computer, even when a computer is used to draw a space curve, optical illusions make it difficult to get a good impression of what the curve really looks like. This is especially true in the trefoil, not this one right here. So from the top view, it looks pretty cool. So this is especially true in the trefoil, not above. See exercise 3 when I go dive into it deeply. And the next example shows how to cope with this problem. This is called, and this brings us to example 7, the twisted cubic. All right, and this one states, use a computer to draw the curve with vector equation r of t is equal to t for the x, and then t squared, and then t cubed for the y and z components, respectively. This curve is called a twisted cube. Interesting. So solution, we start by using the computer to plot the curves with parametric equations. First, I'll just use my calculus book, the graphs, and then I'll go over to GeoGebra. So the result is shown in, this one here. We're going to plot these parametric equations. X equals to t, y equals t squared, and z is equal to t cubed for t is between -2 and 2. So it looks something like this. So the result is shown in the figure below, but it's hard to see the true nature of the curve from the graph alone. So yeah, it's hard to see if it's all in the same plane, and it looks like it's curving up a tiny bit there. Yeah, this one, it does look like it's going up there, but this looks a bit flat. So again, it's hard to tell what if this is a complex shape or just simple one. So most three-dimensional computer graphing programs allow the user to enclose a curve or a surface in a box instead of displaying the coordinate axis. So you could put a box like this. So when we look at the same curve in a box as in the figure below, we have a much clearer picture of it. Yeah, this one right here. So this is actually a box where this goes to the corner, and this goes to the bottom, the rectangular box there. So it looks like it's literally going from a twisted cube like that all the way up from the one corner to the other corner. Like that. So that's pretty cool stuff. So we can see that it climbs from the lower corner of the box in the upper corner nearest us, and it twists as it climbs. Yeah, so it twists right here as it climbs. So it's a twisted cube there. We can get an even better idea of the curve when we view it from different vantage points. The figure below shows the result of rotating the box. to give it another viewpoint. So if you rotate it, it looks like this, so and it curls up like that. So pretty cool setup there. And now this figure, the figure below, or the figures below, show the views we get when we look directly at a face of the box. So this is looking at it directly from the top. So directly from the top is just a parabola. Then if you look at from the side view, it looks like it's a cubic setup there. It's going like this and up. And then looking at the side view, it looks like a inverted parabola, convex parabola like that. From the this is the side with the Z and Y. This one, this was the front view. This is looking at it directly in the front. So that means looking at it from this face. That face looks like that. If you look at it directly from this one, you get the cubic setup there. That's the this is the XZ. So that's the XZ, and then looking at it from the top, you get this parabola. So the top right here, or the bottom. And that's just the XY. There's the XY. So it's pretty cool stuff. So in particular, the top view shows the view from directly above the box. It is here, just fix that up. It is the projection of the curve on the XY plane, namely the parabola y equals x squared. And yeah, that is pretty much because number t is x and y is t squared. So in other words, y is equal to, well, x squared. The side view shows a projection on the xz plane, the cubic curve z equals x cubed, because again, z is equal to t cubed, while x is equal to, and I'll just write that for completeness. So we have z is equal to t cubed, but we know that x equals to t. So in other words, this equals to x cubed. So yeah, so that's the projection on it. It's just a cubic function, like that. And similar for this parabola. So it's now obvious why the given curve is called a twisted cube. So here it is, and just without the box. There it is with the box like that. This is all the views in one place, and there's a different vantage point. And there's the top, there's the front, and there's the side view. Or actually, yeah, no, this one is, yeah, this is the front view. This is the front. That's the side. This is the top. Yes, I think so. So views of the twisted cubic. And here's a graph in GeoGebra right now. I'll open this up. So open that up while it's opening. We'll go back here. So twisted cubic, you can just put that in again. I just made it from a negative 10 to 10. The other one is a negative 2 to 2, but yeah, I could have just done that. But anyways, I made it from a negative 10 to 10. And it goes like that. It goes all the way up. And this is the top view, side view, front view. Yeah, like that. And the exact sides there, I didn't bother making them perfectly aligned, and so on. So if we go back into here, so it should load up. So there's the curve. So you can play around with it. So yes, as good as a box is, but having an actual 3D and then moving it around, because again, my comics book is a bit old, so they probably didn't have this ability. So there it is. That's pretty cool stuff. So again, you can look at it and so on. Oh, actually, it probably did have this, but again, it's a book. So putting this in 3D as a book, and there it is. It looks pretty fascinating. It doesn't look that much of a cube. It looks more like a twisted knot, just a knot. It looks like a knot. All right. So that's pretty cool. And continue further. So another method of visualizing a space curve is to draw it on a surface. And here what I did was I put this header right here just to make it a bit neater. So visualizing space curves on surfaces. So another method of visualizing a space curve is to draw it on a surface. For instance, the twisted cubic in example 7 lies on the parabola y equals x squared. So, because again, in the vertical setup, this is the vertical one, it is a parabola. So it's literally on the parabola from this xy on the vertical side. So if we were to draw it on, the curve is actually on the surface, which is a parabola. So it's on it. So we can see this when we eliminate the parameter t from the first two parametric equations. So x equals to t and y equals to t squared. So if you eliminate it, what ends up happening is we'll just plug in t inside here. You get y is equal to x squared. Yeah, so that just ends up like that. The figure below, and when you have y equals x squared, that means, well, z could be anything. It doesn't matter what z is. It's going to, in other words, z is infinite up and down. So you're just going to have a surface, just similar to that cylinder we had. So the figure below shows a cylinder and the twisted cubic, and we see that the curve moves upward from the origin along the surface of the cylinder. So in other words, that twisted cubic, it's literally just going, it starts off from here. Yeah, it starts off from, where does that go? It starts off from here and goes all the way up. Yeah. So there it is. Yeah, this part right here. And it goes all the way back up there. So fascinating stuff there, indeed. And it's always on that there. We also use this method in example 4 to visualize the helix lying on the circular cylinder. So we already showed that over here. And a third method for visualizing the twisted cubic is to realize that it also lies on the cylinder z equals to x cubed. So this is apparently considered a cylinder, even though it's like a cubic cylinder. So when you have z equals x cubed, we have this cubic setup here as again the y could be infinite all across. So what ends up happening is it's on it, but it's also on, so it's also on then all the way over to the other side, but it's also on the parabola. So in other words, it's on both of them. So it could be viewed as the curve of intersection of the cylinders y equals x squared and z equals x cubed. But again, this views a cylinder. This is a parabolic cylinder, and this is a cubic cylinder. Again, they call those both cylinder. I double checked, and they're right. So, so again, that's what my calculus book calls this a cylinder. I just call it surface. So anyways, so let's graph this in GeoGebra to see this a bit better. So here's a twisted cubic. There's a cylinder with cylinder 1 is y equals x squared. That's a parabolic cylinder. And this one is cylinder 2. That's a cubic cylinder. Z equals x cubed. So first I draw this strictly on the parabolic cylinder, and then this one is on the cubic one, and notice it's on it, and if you put the intersection, it's perfectly on. It's actually quite amazing. So again, this is the epicness of mathematics. Let's continue back here, and the mathematics, you can see the same thing in different ways and basically validate. Okay, this one didn't show up there. I do not know why it did not show up there. Cylinder 1. Okay, so I think it didn't save. So I'm going to have to do it right now quickly, and we'll do that right now. Cylinder 1 is cylinder, let's go write this down here. Cylinder 1, and then this is y equals x squared, like that. Cylinder 2, z equals to also x squared, and x cubed, cubed. Yeah. And there it is. I'm going to save this so that it saves it. No, I thought I saved it. So there it is. That's absolutely epic stuff. So we're going to unhide this. And look, it's on it. And I'm going to close this a bit just so we can see it better. Yeah, so it's literally on it. So absolutely amazing stuff. It's on the other one by itself. And it's on both. And now it's at the exact intersection. So that's crazy stuff there. That's amazing stuff. All right, there we go. All right, epic stuff there, and there's the all the curves. So we have seen that, that's right here. All right, and now let's continue further. And the next section is looking at charged particle or particles, moving in an electromagnetic field. So we have seen that an interesting space curve, the helix, occurs in the model of DNA. Another notable example of a space curve in science is the trajectory of a positively charged particle in orthogonally oriented electric and magnetic field. So if you have the magnetic field this is the B field going up like that, and the electric field going sideways like that, what ends up happening is you're going to have a shape that looks like this. This is, depending on the speed, you're going to have a shape that looks like this, like that. And this is a cycloid, like that. And another shape is you can have it like this, going like this. This is a trochoid, which is actually a more general type of cycloid. So anyways, basically you have this equation right here. This is R for this one here. This is typical trajectories like this. This is where the t minus sine t. You have 1 minus cosine t for the y component, and then t is the parameter t, I guess. And this graph is based on t like this, and this is a trajectory of it. Yeah, this is a trajectory in space, and then with E and B fields going perpendicular like that. So that's interesting. And then there's the this is the other formation depending on the speed of it. We'll get to that in a bit. So this is t minus 3 over 2 sine t. Again, these could be different, but this is just an idea of some typical values. And there's 1 minus 3 over 2 cosine t for the y, and there's t variable there. So a motion of a charged particle in orthogonally oriented electric and magnetic fields. So depending on the initial velocity given the particle at the origin, And yeah, so you have the particle at origin somewhere. Yeah, so it could be like this. Yeah, unless it's going this way. Yeah. So you have the path in the origin like that. There. Yeah, so depending on the initial velocity given the particle at the origin, yeah, and the path of the particle is either a space curve for its projection on the horizontal plane. This is a projection right here. So this one's a projection straight down. This is just at all different angles there. But it's a projection straight down. This is a projection straight down as well, like that. So it's a projection straight down. Yeah, so a space curve whose projection on the horizontal plane is the cycloid we studied in my earlier video, and I'll put out some screenshots here, and there's a link to my earlier video. Or B, a curve whose projection is a trochoid. See exercise 4. So I never covered it before in my earlier chapters, but I will do that at the end of this video. So this is a cycloid. So it's like, recall a cycloid. A cycloid is formed by tracing the position of a point on a circle as it rolls. So you have a circle right here. As it rolls, and then you keep tracing that point, it's going to form it like this. And it's on the point, so it never goes below that. But a trochoid is just a more general version of the cycloid. So the trochoid is formed by tracing any point inside on, hence a cycloid, or outside a circle. So if it's on, it never actually touches the bottom, so it's basically like this. Yeah, like that. If it's on it, you get a cycloid. And if it's outside of it, you're going to have a loop. So it's outside of it, and as it rolls, it goes backwards as it hits the bottom, and then it goes like this. Yeah, so it actually loops around like that. So it's pretty cool stuff there. And I'll show you some illustrations. And I think I have some illustrations. All right, yeah. So here's the trochoid Wikipedia page. This is illustrated in animation form. So this is animation right here. There's a cycloid. It's at the point like that, and it goes straight on it like that. So pretty cool stuff like that. Yeah. So that's a cycloid, just tracing a point on it. And we go to the next one. Next one, this is a trochoid, but they call it a prolate trochoid, which is basically extending past it. And it loops around like that. And then the other one is a curtate trochoid. This one doesn't, it's inside the circle, point inside. So it goes like that, never touches the bottom. There's no sharp edge or loop. So that's pretty cool stuff. All right, let's continue back. All right, so we have this. So note, some computer algebra systems provide us with a clearer picture of a space curve by closing it in a tube. So here it's, this one right here, it's hard to tell how it's looping and so on. But if you put in a tube, you can see it in 3D, which form it's going. So, so such a plot enables us to see whether one part of a curve passes in front of or behind another part of the curve. And the figure below shows the curve of B as rendered by the tube plot in two-plot command in Maples. It's just a mathematical program. Just a pretty advanced mathematical program and graphing setup there. So this is the tube here, and this is the graph, and they put a tube there. So now you could see that it loops around this way, or if it's starting from the origin. If it's starting from the origin like this, it loops around like that. So yes, pretty cool stuff there. And that's in 3D, so you can see in which one is overlapping which side. And here are the graphs in GeoGebra. So there's the link there. Let's open this up. So it's going to be a pretty big graph right here. I'm going to close some stuff here. All right, so we close some stuff, see if it's loading. And while it's loading, let's go back here. So here's the graphs in GeoGebra that I put in. So note the graphs are plotted when z equals 0. Still match those in blue because of symmetry. Again, this was actually before I realized it's a projection. I'll just erase these. This is, don't need to write that. So basically, the ones at z equals 0, that's just a projection. Yeah. Cycloid XY, that's a projection. Because it's, the calculus book already said that. Yeah, so it's, so basically we have the trochoid right here. I put those parameters in. I put the components, and then I made it from T, made from 0 to 12 pi, just whatever until a decent setup there. And a cycloid, and there is a cycloid projection on the XY plane, where the Z is 0, and there's a trochoid on the made Z equals 0. So there's a cycloid, T minus sine T, 1 minus cosine T is again same thing, but then I set up the 0. And here's the graph, how it looks like. So it looks like this. I put them both together, and you can see it like that, and you can see them plot them out separately. There is the cycloid one. If you project it straight down, there's a cycloid shape. And the other one, if you project this one straight down, you get that trochoid setup there. So since there's no tube command, and also this also is interesting as well. So it's still loading. It's not loading. Okay, there it is. See the algebra. Do I have the algebra? Okay, the algebra setup is pretty complicated. So I'm going to go right here. I'm going to go all the way across here. And so this is the cycloid. I will unhide this one here. So there's a cycloid like this. And then you can see the projection straight down. And there it is in 3D like that. So again, it's hard to see, but you can see it loops around like that. It's decent. And then there is the cycloid. Let's go to the trochoid. So there's a trochoid, put it straight down. So that's again, that's exactly what we get. So there's a looping around effect like that. And so since there's no tube command in GeoGebra, so I can just put tube, make it a tube similar to this one. There's no tube command, but instead, since there's no tube command, I use the surface command via Grok AI. So just using, I asked them, make me a tube command or tube setup or similar tube setup on GeoGebra. To generate a circular cross section of the curves. There's what it made up for me, and it basically the whole idea is to simplify it. It looks giant, but basically it takes these curves. For example, here is the I'll do the cycloid. Actually, I'll do the trochoid. There's a trochoid. There's a trochoid surface, and I'll do the trochoid and the XY. So what it does is I'll take that curve, the surface. So basically trochoid surface, and it puts these in. But I also included this setup here, what Grok AI added, this 0.2 cosine u, it added a third parameter, and this one is just literally just going from 0 to 2 pi, where 0 to 2 pi. All it is just making a circle around it, cross section. Again, this is all super complicated. I didn't want to. It's not that complicated if you break it down, but anyways, it's outside of this video. And again, there's this shape there. All it does is create a circular cross section. I do this in another exercise. It's in a bit simpler one, but that one was just super advanced. So there it is, and it's notice all the calculations being put into it, and you can see it loops at the bottom and up, loops in bottom and up. And if you scroll all the way in, you can see you could kind of see that cross section circular surface that it made. So basically, what it does is at every point it adds another parameter, and it loops around in a circle. And yeah, so there's it's a circular setup like that. But I think I made the X and Y axis not in sync, so they're a bit out of shape. But anyways, it's just too slow to figure this out or make it a bit nicer. But anyways, that's the general idea. So that's that. And then again, I added the Grok AI added this extra term right here. Whoops. Yeah, this added this extra term, the U, to every single one, and it also puts it out like here. So it adds all these U parts right here, and this is all just to make a cross section circle surface. All right, and that's what we have here. Yeah, so we have this one is for the cycloid. This is a trochoid, and I want to do it right here, just for completeness. Go back to the algebra. Okay, a lot of times a bit slow because this is a giant calculation. There it is. This cycloid and then cycloid surface. And actually, I do want to make this. Here, I'll want to see if it makes it better. What I'll do is I'll do the settings. So I'll make this -4, just so that it's all the same size. This is -4 to 4, -4 to 4. So it's all the exact same scale. Okay, so it scales up like that. Yeah, so you can see how it makes it a circle. It makes a circle from this cross section, and I'm not sure how it changes that well. But anyways, that's that. I'll make it even a bit more, just so it's exactly the same length there. So this is the Z 0 to 4. How does that work? Yeah, to make it exactly the same size, I'll scale up one more try. I do want to make this nice. What I'll do is 0, x0, 10, 0, 10, 0, 10. Okay, let's see what happens now. So it's always the exact same. Yeah, so it's a pretty cool shape there. And this is the cycloid one. That's the thing. It's a cycloid. Under the trichoid surface. And this is pretty cool stuff. Anyways, yeah. So that is pretty cool there. I just made sure that the scale is the same thing. So yeah, it is like a twisted setup there. Pretty cool. Anyways, and there's the setup there. Alright, so anyways, let's go further. And this one here, we're going to look at the physics of charged particles in electromagnetic fields. And this one, it's more for my sake. I just want to learn a bit more. But again, this is from my calculus book. It says, for further details concerning the physics involved in animations of the trajectories of particles, see the following website. So include a link right here. This one right here, note that to run this website, you'll need to run Java applets, which apparently all the new browsers don't have anymore because of a security issue. But you can download a browser extension that, like this one, I downloaded it and it works. So this one here does not have this anymore. So this one, if you can see this, it means your browser cannot run Java applets. Please upgrade to a Java capable browser like Netscape 3.01 or Windows 3.1. So again, this is like decades ago. I'm gonna download this quickly. It's on my laptop. I had it on my other one. But anyways, when you download it, it looks like this, and we'll do some testing out. So this is magnetic field going up on the Y, and there's the electric field going this way, and then the shape goes up like this. If you have just the magnetic field, it just goes in a circle or something. Oh, actually, this is graphing T. No, that's yeah. If you just have it magnetic field itself, it might just go in a circle. So anyways, so that is what we have there. I'm gonna go download this quickly. Add the Chrome. I'm using Brave browser, but it should work. Yeah, but they're both Chrome. Okay, I'm gonna add this quickly. Add this, and let's see if I can run this. Oh, it's downloading. Alright, so I downloaded. It should run now. Let's see if I go right here. And so on. There it is. Let's go over, pin this, and go here. Charged particle motion. I just want to show this. This is a pretty cool site. Apparently, it's hard to do. There isn't any modern sites that do both of these on there at the same time. Besides, like some advanced ones, they either have to pay or sign up and all that stuff. Okay. Enable for this domain. Alright, here it's loading up now. It took a while to load up, but anyways, there's the loading up right here. So it's charged particle motion, and then there's a bunch of stuff here on what it does. And again, I don't want to go through it all. It basically uses Lorentz force on Lorentz force acting on a point charge. Q is given by this equation. It goes over the equations. I'm just gonna go start right here and see what happens. I'm gonna zoom in. So it's going up, and I think it's gonna go into cycloid as we keep going. Yeah, so let's keep going. Let's see what happens to this shape right here. So again, it's doing a lot of mathematics. I think it's just going to be a cycloid in this case. So again, depending on the speed and so on, you're going to get different setups. So there's a cycloid particle going in an electromagnetic field. It's from like decades old software. But anyways, I want to illustrate that. Okay, stop. Okay, it doesn't stop. There's a stopping. And so, and again, you could play around with it, and so on. You get a cycloid, and see if you can get the trochoid. So anyways, this is from the other link that they added here, and it's pretty extensive, but it's a bunch of experiments, but I do want to read this for completeness, and also, so again, I'm going to read this all, and then some of it I'll need to review later, but again, this is for my own sake. So, single particle motion in electric and magnetic fields. So the following photographs were made in the Physics 180E undergraduate 180E undergraduate laboratory course in plasma physics by Professor Rainer L. Stenzel. They are designed to demonstrate the single particle motion in electric and magnetic fields. A weak electron beam of 100 electron volts, and then from 1 to 10 milliamps, is injected from an oxide-coated cathode. So the cathode is the positive end, I believe, and then the anode is the negative. Into a low-pressure 0.2 millitorr. It's like vacuum argon gas. The beam partially ionizes the gas, so you get the free charges. The background plasma has a potential close to that of the grounded chamber wall. The beam electrons are accelerated by an electric field mainly concentrated in the cathode's sheath. Interesting, and the trajectory of the beam electrons is visible due to light excitation when the beam electrons collide with argon atoms. No visible light is produced when the electron energy is below 10 electron volts. Yeah, that's EV electron volts. Several basic phenomena can be inferred from the following pictures. These were taken with a Rolleiflex camera, 400 ASA, black and white film with up to 1 minute exposure time. So again, it's pretty ancient tech here. So this is a plasma setup there, basically just a bunch of electrons. Figure 1, a 100 electron volt electron beam is ejected into a neutral gas or argon without applying external electric or magnetic field. So there's no electric or magnetic fields. It looks like this. Interesting how it dips in like that and then pulls it out. The beam starts very close to the cathode, indicating that the electrons acquire their full energy in a very thin cathode sheath. Thus, the self-produced plasma acts as an anode, so the negative side. The initial beam converges indicates concave equipotential surfaces near the cathode. Interesting. I gotta read up on this. Near the cathode, presumably due to a radial density gradient. The beam scatters by collisions and beam plasma instability. So interesting. So beam plasma is unstable and expands out, but it looks like it wants to compress again. So that's pretty fascinating. And now here is figure 2. So, or did I miss figure 2? All right, here, yes, I actually did miss figure 2. And here's the actual original site here. Here's the original one here, single particle motion from the UCLA website right here. And yeah, so I just basically copy and paste the text and the images, and because I think it's very valuable information. So the beam is ejected against a negatively biased grid. When the bias voltage is slightly larger than the cathode voltage, most of the beam is reflected, but a few electrons are transmitted, so it goes through. Note that the equipotential surface near the grid is not a plane, but a convex. Interesting. So it's this one here. I think is that what they're talking about here? It's a bit convex, not yeah, it's a convex. This causes an angular spread of the reflected electron. So yeah, there it is. It spreads outward like that. Electrons in the center of the beam are normal to the sheath and can pass the grid when their energy exceeds the potential energy of the sheath. So it goes through it like that. Fascinating. And then going further, yeah, this is yeah, this is. Oh, actually, I put this above this. Okay, this is figure 1. This is figure 2. Let's put this, let's fix this up quickly. Alright, and copy and paste this right here. Alright, so that's that. And now the next one is right here. So beam injection against a very negatively biased grid which reflects all electrons. So because electrons are negative, hits a negative, and it reflects a lot. No dark sheath near grid where the electron energy is decreased below 10 electron volts. This is a dark sheath near the grid. I think is this what it means right here, the dark one. I'm not sure what that is. The electrons stagnate in the dark sheath and form a convex equipotential surface. This causes the reflected beam to be highly divergent. So convex. So I think it's shooting outwards like that. Or is it actually talking about this one here? Stagnates here, so it's concave surface. And I'm not 100% sure, but this is pretty cool stuff here. And then here's the loop right here. So this is a 100 electron volts electron beam injected perpendicular to a DC magnetic field, so direct current magnetic field. So not alternating current, just direct current magnetic field, and this is perpendicular to it. So if this is shooting like that, so the magnetic field is either this way or this way through it, and it's using an electromagnet, DC magnetic field. The sense of the cyclotron orbit implies the magnetic field points into the plane, so into the plane like this, and that is the sense of it. Again, I think that's just the way how it looks like. And the beam energy and the cyclotron radius. From the beam energy and the cyclotron radius, the field strength can be calculated. Note that the beam light weakens with propagation distance. And this is the cyclotron is basically, I think it just means this right there. Again, I don't have time to double check everything, because I wanted to include this for my own research during this video making. And I think there's 12 images. I'm going to go over some of them. Again, these are all fascinating. So figure 5, a low energy beam is injected across a magnetic field as in figure 1. As in figure 1, there was no magnetic field. So this one here is injected here. This one has no magnetic field. And this one, I think it might have made a different one. Okay. So, as in, it might be saying figure 4. Figure 4. I'll put the code. Fig 4 question mark. Okay. Because that's this is. Yeah, because this is it looks exactly like that. Well, it's different, but it's the figure 1 didn't have a magnetic field. Figure 4 did, and it looks like similar. So the cyclotron radius is decreased. Note the dark gap between the cathode and the beam onset. In this sheath region, the electrons still have insufficient energy for light excitation, and that's just right here. So they don't have enough energy to excite light in the argon gas. And then, yeah, so again, that's what it means there. So again, I think that's what it's talking about, this convex part right there. I think that's what they were talking about. Anyways, so that is fascinating stuff. So this one's less energy. All right, going further. A low energy beam is injected against a decelerating electric field. Interesting. And I think it's perpendicular as well. As the beam energy falls below 10 electron volts, the light emission stops. So it doesn't have any more emission past this. It doesn't excite the argon atoms anymore. The beam and current continue to flow through the dark region. So the beam and current still goes through, but it doesn't have enough energy to excite it. So that's pretty cool. That's an electric field. All right, and going further, at neutral pressures, the injected electron beams rapidly spreads. This is at high neutral pressure. So this is at high pressure of the argon gas. I believe that's what it means. The electron mean free path can be inferred from the beam decay. And again, it's like after this point, it just spreads a lot when pressure is high, because it's hitting a lot of the argon gas. So here's a figure 8: electron motion in crossed electric and magnetic fields. So I think what it means is perpendicular ones. You have electric magnetic fields in perpendicular setups like this. I think that's what it means. And then there's our trochoid. The trajectory is a cycloid, is actually a trochoid. Superposition of a circular motion, a constant drift to the right. This should be a trochoid. A cycloid is a specific type of it. I think, or trochoid, I think. Or it should be just more general trochoid. I.e. a superposition of a circular motion at a constant drift to the right. The cyclotron orbit implies a magnetic field direction into the plane, so it's going into it. So this means going in, if you draw a dot like this. Going into it. No, actually that's going out. Into it would be like this. Yeah, this is going into the page. Think of it as an arrow. I think that's how it is. Into the page. So here I just quickly googled magnetic field into and out of page sign. Let's see which one is into and out of it. Yeah, out of page, into page. Yeah, that's the X. And you can think of it as like the this is the tip of an arrow, and this is like the bottom of it. Okay, so this is into the page, and yeah, so into like that. All right, so that's into. I'll just erase it. So yes, okay. Implies a magnetic field direction into the plane, and E cross B drift implies the electric field points downwards. So yeah, so this electric field is going down, E is down. And then into the page is the B field, or the magnetic field. Typically they call it B. Like that. So the down and the other one like that. Interesting. So it's saying that the E going down implies the drift. This is what's going down around where that electric field is. So if it's pointing down, electric field is going down. I mean, if it's going down, electric field is going down. Possibly. From the known beam energy, the field strengths can be obtained from cyclotron radius and guiding center drift. So you can calculate the beam energy and so on. And there's a drift. So that's pretty fascinating stuff. There's an electron beam spread there. Here's some more cool stuff here. So mirror reflection of a weak electron beam in a non-uniform magnetic field. The beam is injected oblique to the field lines, so at a different angle, which converge to the right due to the adiabatic invariance or energy and magnetic moment. The parallel energy is converted into perpendicular energy, at which point the particles reflect. Alternatively, the parallel motion is decelerated by the repelling force of an increasing magnetic field. So again, I'm not 1000% sure, but it looks like it's going like this around there. But it says there's a mirror. Mirror reflection of a weak electron beam in a non-uniform. So it's like a reflection there, and it goes backwards. Yeah, so it goes like this and hits backwards. The beam is injected oblique to the field lines, will converge to the right. And this is due to adiabatic invariance or energy magnetic moment. The parallel energy is converted into perpendicular energy, at which points the particles reflect. So it reflects off this, it goes over to this side. Again, non-uniform magnetic field. Alternatively, the parallel motion is decelerated by the repelling force of an increasing magnetic field. Like, interesting. So it's a non-uniform. It might be stronger over here, and pushes it outward. So again, I'm just trying to infer from this, and for future reference. And if you're an expert on this, let me know any statements you want to clarify. So here's another setup here. So mirror reflection of a stronger magnetic field in a magnetic field which converges to the right. Interesting. So I think it's like a magnetic field that's converging all the way here and getting super, super strong. So then it repels that electron beam or something. I'm assuming that's what it is. Note that the guiding center axis of spiral of the reflected beam does not coincide with that of the incident. So note the guiding center axis of the spiral does not coincide with that of the incident. This is due to the gradient and curvature of drift in a non-uniform field. So it's actually, I think it's saying that this does not align with this axis right here, and this separates. I think it cuts off there, but again, I'm not 100% sure what that means there, and so forth. Anyways, I might review it later when I upload the sections video of this. I go further. Full figure. This is figure 10. Figure 11. So again, I should include this because this is a pretty epic electron beam movement, and again, you can see that trochoid motion there. Figure 11. Multiple reflections of an oblique electron beam in a mirror magnetic field. Mirror magnetic field. Okay, this one's interesting. Mirror magnetic field. I think that's the whole key there. I've never heard about this in my life, so I'm going to Google this. So we're doing live research right now, guys. Magnetic mirror. Magnetic mirror. Particle motion right here, and then current, and it basically, this is, I'm not sure how it's mirroring. Again, I just want to see one more setup here. So speed is no longer parallel to magnetic field. So it goes like this. Yeah, initially it's parallel, and then it's, yeah, I think it's like condensing here. So now it's not parallel. Now speed is no longer parallel, so it's condensing it. So that's amazing stuff there. So I think it, yeah, does make it a different, right? Let's go right here. Magnetic trap. So again, I've never heard about this. A magnetic mirror, also known as magnetic trap, or sometimes a pyotron, is a type of magnetic confinement fusion device used in fusion power to trap high temperature plasma using magnetic fields. The mirror is one of the earliest major approaches to fusion power. Okay, interesting. Now we're dealing with magnetic fusion. So it basically has different strengths across it, I think. Okay, so I will have to review this later there. The mirror effect only occurs particles within a limited range of velocities and angles of approach. All right, I'm going to read this right here. So in a classical magnetic mirror, a configuration of electromagnets is used to create an area with an increasing density of magnetic fields at either end. So you basically have super strong at either ends. With an increasing density of magnetic field lines at either end of the confinement volume, particles approaching the ends experience an increasing force that eventually causes them to reverse direction and return to the confinement area. So basically it's like, yeah, it's literally a magnetic mirror. So multiple reflections right here. In an oblique electron beam in a mirror magnetic field, the cyclotron motion is the fastest periodic motion, followed by the slower bounce motion between the mirror points. So there's the cyclone, it's super fast, and all of a sudden I think it bounces off here, and bounces off that magnetic mirror there. And slower bounce between mirror points. Gradient and curvature drifts causes a third slowest rotation azimuthally around the mirror axis. This is the classical charged particle motion in the ionosphere in Earth's magnetic dipole field. Collisions and other scattering processes diffuse the beam. So this is the setup what you see in when charged particles are in the ionosphere in the Earth. You're going to see those northern lights and so on. And I'll talk about that in a bit. So again, this is a lot to digest, which I will do in a future video or live stream. Okay, so here's another setup here. This is the last one. Figure 12. Electron beam injected into a non-uniform magnetic field with a null line. So I think a null line has no magnetic field there. I'm going to say, I'm going to ask Grok right here. Okay, so here's Grok. So non-uniform magnetic fields with a null line. What does this mean? Okay. First, a magnetic field with strength that varies in strength and direction across space uniform contains a specific line or region where the magnetic field is zero. So that's what it was. Yeah, so the null line basically zero. With a null line, the beam meanders along a magnetic null line pointing diagonally down to the right. So you have a line like this that has, I think that is this what it means? It's meandering it. Whoops. Yeah, I think it means like. Oops, again, it's doing that. Yeah, so I think it's going like this. Is that where it is? Again, if they drew some lines that indicate where in the world is this null line. Diagonally down to the right, note the reversal of the cyclotron rotation as the magnetic field reverses to either side of the neutral line. Such meandering and figure 8 configurations have been studied theoretically in the problem of magnetic reconnection occurring in the magnetosphere and then on the sun. Interesting. So then you have a point of no magnetic field right here. It loops around like this. And but where does it go? Beam meanders along. It meanders along a magnetic line. So, but then where's the magnetic line like that? So then, where's the magnetic? It's going down to the right, pointing diagonally down to the right, But where in the world is it? Is it up here? All right. Anyways, this is for future study. But hopefully you enjoyed this reading up in there. I'm going to read a bit more. This is first. Here's an amazing charged particle in a magnetic field 3D calculator from that Tom Walsh made in GeoGebra. So this one made it. This is in a magnetic field. There's no electric field in this, so it just loops around in a circle. So I think the electric field will cause it to drift in that area, in a specific area. So if we go back here, this one here. So the magnetic field, this one here, so it's drifting across to it, and then it's moving it, but it's pushing it this way, and then yeah, it's basically going towards the magnetic field, but the electric field is pushing it, and then as the again, I'm not 100% sure how this all works, but anyways, so here's a setup right here. So if I press play. This is a magnetic field, and it's going up. Yeah. Oh, whoops. This is a play. Okay, there's a play. It's going in a loop like that. And if you show magnetic field is going up. So this is a particle going in it like that. You could change this setup here. The stuff here, you can change the animation speed. This is the B setup there, the M, and other show velocity. And you can also show the velocity here. This is show magnetic field, show particle path. And then reset. Let's see the reset. And there's the arrows like that. So there's the arrow of the velocity vector. Anyways, so that's that. So it's pretty cool. Want to include that. And note that a moving charged particle experiences what's known as a Lorentz force from a magnetic field according to the right-hand rule. Here's a video on that path of charged particle and magnetic field, moving charges and magnetism. So this one is pointing into the page. Yeah. So I'll draw this with a white line, or actually. I'll draw this with a blue. Yeah, okay, so that's a blue. Yeah, so this is going into the page. So this is pushing it straight down. And what happens is you use your right-hand rule. You curve this in the direction. You point your fingers down. So it's pointing down into the direction. This is going straight down into the direction of the magnetic field. And then the force that this is, I think, a positive charged particle experiences that's moving. Is going to be to the right. So this is one right here, and this is moving forward like here. Yeah, no, I think the way it works is this. You put your thumb in the direction of the velocity. This is the velocity of the charged particle. And then you curl your arms in the direction of the magnetic field. So in this case, it's going into the page. And then using your right-hand rule, the thumb pushes this sideways. So pushes the force sideways. And then if you keep doing that, it's going to go around in a circle like that, in a circle around this. This is just a magnetic field. Let's see further. And then here's some more stuff right here. So here's illustrating it more. So as it, and then as it turns, so particle goes in a circle. So V is perpendicular, the velocity vector is perpendicular to the B vector. And the Q is the amount of charge. And this the V is the velocity in this magnetic field. It's a cross product using it. And as it goes here, you're always going to turning your hand. And so it keeps going in a circle. And then in general, this one is, and this one here is in a helix one. This is going at an angle. This is a magnetic field going perpendicular to it, but there's no electric field. This one, but if it goes at an angle, you're gonna have it going in a loop like that. If it's starting off at an angle. If this one, if it's just starting off initially as like that, then it goes. If it's starting off perfectly perpendicular, magnetic field, it goes like that. And then it goes further. In general, helix path, just because not everything goes perfectly in line with that magnetic field. And then the Earth's magnetic field is like this. So then the particles get trapped it goes in a cycloid and gets trapped in these areas, and that's where you get these northern lights typically show at the poles. So yes, that's fascinating stuff there. And here's another video, right-hand rule video. Another way you can look at it, you can have the velocity vector pointing with your finger, magnetic field pointing down, and then this going up, and then the force is your thumb. So you can do that as well. And here's another illustration. This is from Wikipedia. And the link to the Wikipedia one right here, I think I put a link. This is a Lorentz force right here. So that click that link there. These are the images. So if you have magnetic field here pointing out of the page, a velocity here. If you have Q, a charge right here. If its charge is positive, it curls like this. If it's negative, it goes opposite way. So if it's your thumb, I think this is for positive, and then the negative would be just going downward. So curls up like that. And if it's zero, if there's no charge, it goes straight. So trajectory of a particle with a positive charge or negative charge, Q under the influence of magnetic field, which is directed perpendicular out of the screen. Hence this arrow pointing up. And here's another setup right here. Again, I told you this would be an extensive electromagnetic setup here. A deep dive. So beam of electrons moving in a circle due to the presence of a magnetic field. So here is a beam of electrons moving in a circle. Yeah, this one here, beam of electrons going in a circle. The magnetic field is going perpendicular to it. Purple light reveals the electron's path in this Teltron tube. It's created by the electrons colliding with gas molecules. Again, if colliding with it, that's the light that's getting excited and emitted outwards, as I went over in that previous paper or previous article. So here's another. I'm gonna go lower here. So here's a charged particle drifts in a homogeneous magnetic field. So A is no disturbing force, and then B is with an electric field. Let's go right here. So this is A. Where's the A one? There's no A. Yeah, there's A. There's A right here. So here is this is the magnetic field pointing out of the page. So magnetic field points upwards through the page. It's basically pointing out to. It's basically pointing out to you. All right. So it's pointing out to you. Make this back into the black. And so if you have a negative one, it spins this way. So you use the right hand rule. So if it's initially starting off, I think it's like use the right hand rule, the thumb. Yeah, I think this is it's called magnetic field like this. I'm trying to illustrate this. Oh yeah, here I think I got it. So I'm going to use this right here, this setup right here. So if you have your thumb, yeah, the thumb is the force. But if you have your index finger, I'm gonna see if this right here. So this looks like that. And this is going in this is the initial direction. So if this is the path of it, and then your middle finger is going like this. This is your and this is your rest of your fingers. Yeah, this is your other 3 fingers like this, and then your thumb would be sideways. Yeah, this is your thumb. Yeah, or this is the thumb. So in other words, if this is going up like here, that's the velocity. The magnetic field is pointing out right here. So in other words, the thumb is going to point to the right. So this one's going to go to the right and loop in a circle. But then if it's a negative, it's the reverse setup here. So in other words, if it's going this way, then it's going to be rotating this way here because the force is going to be acting on the other side. Again, hopefully you grasp that. And that's just right here again. That's just right here. And then reverse it with your left hand. All right, so anyways, so this loops out around in a circle. Charged particle drifts in a homogeneous magnetic field. A, no disturbing charge, it just loops in a circle. B, with an electric field. Yeah, so let's look at B, what happens with an electric field. So if you have an electric field going down like here, this one's going up. Yeah, so now it's going to be the positive one will loop like this. So it's pretty fascinating. And then a negative one, if a negative charge will be going, let's see, yeah, instead of looping up like this, it's looping down. Yeah, so these are both drifting on this side, and it's gonna go like this. And this one is going up, so basically goes opposite direction of that. And then if you have what's another one? With an independent force. F, this is gravity. So if you have gravity going down, so this one's pretty cool. So this one, and if you have gravity, and it's the same thing. But this one is going the opposite direction. Okay, this is going opposite direction. Interesting. So drift is going, if you have the gravities going down, it doesn't reverse the peaks like that. It just goes in a different direction with the force of gravity there. And now going further, in a homogeneous magnetic field or gradient H. So if you have a stronger field going up, so if you have, basically you have pointing a magnetic field super strong over here. So super strong and then super little right here. The setup is similar to gravity. All right, so this is identical. So gravity is gravity right here. Yeah, here I just want to write that again. So is gravity just a magnetic field gradient? Magnetic field grad. Unbelievable! I think we just solved this right here. So it's pretty interesting here. It looks exactly the same setup for the charged particles. So yes, fascinating stuff. Anyways, that's something to think about. And here, MES note, is gravity just a magnetic field gradient? All right, I know, it's just observing it quickly, but yeah, I think it's I think it's something more than just that, but I definitely think they're connected in some ways we're not being told. Anyways, it's epic stuff there. Alright, now let's take a look at the exercises, and starting off with exercise 1, and this is on the precise definition of a vector function limit. And we're asked to show that the limit t, as t approaches a of the vector function r of t is equal to b, the b vector, if and only if for every, these are Greek letters, epsilon greater than 0, there is a number, delta, greater than 0, such that if we have this interval where t minus a, the absolute value of it, is greater than 0 and less than delta, then this interval right here, the vector function r minus the vector b, the difference, is less than epsilon. So basically what it's saying is that we can make this as small as we want as long as it's positive, and then this will always have the scenario. We will always have a t value. A t value that's basically if you make this really small, you can make this this interval also really small, but again positive, but not exactly 0, but all you can make it almost equal to 0, and this interval gets smaller and smaller, t minus a, and then you'll always have the scenario where this r of t minus b vector, they're always going to get smaller and smaller. Basically, the difference between the two goes to 0. So in other words, if the difference is going to 0, the limits are equal. So they're approaching each other in value. And here's to illustrate that. We'll do a quick recap before we go over to the solution. So recap on limits. So recall the precise definition of a real valued function from my earlier video. So here's the definition. Let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that the limit of f of x as x approaches a is L, and we write limit as x approaches a of f of x equals to L if for every number epsilon is greater than 0, there is a number delta greater than 0, such that if we have the difference right here, the interval x, the difference or interval x minus a, the absolute value is between 0 and delta, then the difference between the function and the limit is going to be less than epsilon. So, and this one we can make this this is for every positive number epsilon, so we can make this infinitely small, and then this will still be satisfied because this gets infinitely closer to this. In other words, the x value, we will always have an x value that we plug this in. This becomes infinitely small, and this gets infinitely small. And in other words, these are all approaching each other, or this one's approaching the limit. So, and we'll illustrate that right here. So here's an illustration of that. So what we have, I'll just zoom in right here. So if we have right here, this is at A. So let's say this is our number right there. Yeah, so this is at A, and then there's the limit L, like that. And basically what these intervals mean, so now if we have this interval epsilon right here, and this is our function f of x. Yeah, this is y equals f of x. This is, I used the AI upscaler, I kind of messed up that equal sign. This one wasn't that good of a quality image. But anyways, what happens here is, yeah, so this interval right here, this is f of x minus L. So if we have L right here plus epsilon, and then, so this is the interval right here. This is basically f of x, or actually, this would be right here. F of x minus L, like that. This is going to be less than epsilon. Alright, so it's between that, but then it's, and then if you have it also on the negative side, so you can also have it over here, this interval, and this is because the f of x could be higher, it could be lower, etc. You could have it over here, you could have it over here, so then this difference is going to be epsilon right there. And as we get closer and closer to A, if the limit exists, then basically all that ends up happening is, so that's the A value. We'll go over here now. So we know f of x is in here. And now if we shrink the interval, this is the delta now. So before it's epsilon, the delta is dealing with this x variable right here. So when x is in here, and x is not equal to A, just approaching it. So as you're approaching it right here, you're always going to have a scenario. Yeah, you're always going to have a scenario where f of x is always going to be within here. Like that. And in this case, right here, we're using this one as the maximum one, and then hence why it's over there. But then if we go and shrink it even more, what ends up happening is, well, we shrink it all the way even smaller, so then what ends up happening is the intervals becomes even smaller there. So now this is the epsilon. So as we shrink it, and then eventually you basically get all the way to this point. So in other words, we can get smaller and smaller, and there will always be this epsilon value, and a corresponding delta value. That just all they do is get smaller and smaller until we get to like all the way up to here and here. So the interval is going to be there. In other words, it's approaching that value. All right. So I just want to recap on that. Also, for my own sake, it's been a while since I covered that in a precise definition of limits. So now let's take a look at solution 1. So now we're going to do this for vector functions, and instead of dealing with limit L, a real number, we're doing this is the limit B is going to be a vector, and instead of this is a function, this is a vector function, and so on. And this one here, instead of x minus a, we have t minus a, where t is a parameter. All right. So solution 1: let R of t be a vector defined on some open interval containing t equals a, except possibly at a itself. All right, and let B be a vector in R3. In other words, basically in 3D. Right here. So let's write this out, and also basically so let's write these down. So R of t is equal to, so basically it's defined on an open interval. The open interval is basically just the endpoints. It doesn't need to equal or it goes infinity, etc. So we have it like this. This is going to be containing, and this is going to be, we're just going to write these in component parts. I'm going to write this as, so let R of t vector function equals to the component parts f of t, g of t, and h of t, like that. And we let b, so we let that, and b, the b vector of t is equal to, this is going to be, this is, this is just a vector. It's not b of t. This is just a straight vector b, like that. So this is equal to, we'll have real values b1, b2, b3, like that. All right. So in this solution, what we'll do is I'm going to write if. So if we have, if the limit right here, as t approaches, so we're just going to assume it's true. So if the limit as t approaches a of the vector function R of t is equal to b of t, then what this means is the limit exists. Then limit, let's write that here. So if it's equal to that, then the limit has to exist. And this is going to be limit R of t exists. And if the limit exists, then, well, thus, by definition 1, we're going to have, and if we recall definition 1, I'll just jump over to, so here I just jumped over here. So this definition 1 is going to, so if the limit exists right here, or I mean, if you have a vector function right here, R of t equals f of t has components f of t, g of t, h of t, then if the limit exists, then this is by definition, the limit of this vector function is equal to the limit of its components, the limit of f of t as t approaches a, and so on. This limit of g of t, limit of h of t. All right, so that's by definition 1. I'll just teleport it over here. So limit as t approaches a of R of t, this equals to the limit as t approaches a of, this is going to be f of t, limit as t approaches a of, this is going to be g of t, and limit as t approaches a of h of t, like that. Alright, so now we have this by definition, but we also know that, well, we're told right here, so we're starting off if this equals to b, so if these vectors are equal to each other, so well, by definition of just basic equal vectors, this has to equal to, this is b1, because it's equal to the b vector, so this has to be equal to b1, b2, b3, like that. So what I'm going to do is, so then they're equal to it, thus we're going to have 3, so then these ones have to be equal to them. Now we have 3 different limits that don't have the vector function anymore. So we are going to have limit as t approaches a of f of t is equal to b1, and I'll write this down over here now, limit as t approaches a of g of t, this equals to b2, and finally limit as t approaches a of h of t equals to b3. All right, but right here, these are these are limits of real valued functions. So by the definition of limits, for every epsilon greater than 0, there exists delta 1 greater than 0, delta 2 greater than 0, and delta 3 greater than 0. So 3 greater than 0, such that, so we're going to have such that if let's put this right here. So now we have the interval right here. This is, again, this is going back to the limits. Recap on the same thing here. So these are just real functions. So now this is where we're going to have epsilon and delta. But instead of writing epsilon 1, 2, 3, I'm just going to go epsilon divided by 3. That's my solutions manual laws. So we're just going to have write this right here, interval x minus a between 0 and delta. And now we'll have this. Then we're going to have f of x is going to be less than L. And this is between here. Now, yeah, less than L, I mean, the difference is going to be less than delta. In our case, we're going to just divide it by 3, and it'll illustrate why. So we're going to go right here. This is t minus a. This is delta 1, then. And in our case, then we're going to have now the difference between f. Now, this is for here, f of t. Minus the limit is b1 now. These are just regular numbers there. And this is going to be less than, and we're going to write this as epsilon divided by 3, just because we need to equate these to the real value function limit. And here there's 3 components, so we're just going to divide these all out in thirds. But again, remember, epsilon could be any number, so it doesn't really matter too much. It just gets smaller and smaller. But here we're just going to divide it by 3, just because we have 3 components, and so it'll be a bit more accurate. If we were to graph these all out, if we actually get real values for them. Anyways, the second one is going to be, again, t minus a less than delta 2, then g of t less than b2, and that's just this one right here. That's going to be for every number epsilon, epsilon divided by 3, less than epsilon divided by 3. And I'm going to write this a bit better. Now the next one is if. Alright, so if 0 less than t minus a, and then less than delta 3, then we're going to have h of t minus b3 less than epsilon divided by 3. Alright, so just divide that out. So we could have done epsilon 1, 2, 3, but we'll just divide it by 3 in this case. And it's the same thing. These are still epsilon 1, epsilon 2, epsilon 3, but they're all just equal to each other. All right, and so now what we'll do is we'll put these all together. Again, you'll realize why we had this divided by 3. So basically, we're going to sum all these up because we want the full summation right here. Because we want to deal with the vector function right here as opposed to just the components. So so these are the individual components as limits. So now if we let delta without a subscript equal to the minimum of the delta 1, 2, and 3. This is going to be 3. Yeah, so we'll take the minimum of it, so that, again, these could be any numbers, but we'll just deal with the minimum. And so and if it's the minimum, then that fits every requirement. So, for example, if this is the minimum, then this will still be less than S1, delta 1, delta 3. So these will all fit. So we'll take the minimum of it. Then if we have, we have 0 t minus a, and then this is the absolute value of t minus a is less than delta, then we're going to have, now if we sum all these up, so we're going to sum all these up, f of t, and then plus g of t, this f of t minus b1 absolute value, plus this one, we're going to get is a minus b1 plus g of t minus b2 plus, this is h of t minus b3. This is going to be equal to Well, actually, it's going to be less than. Less than E3 divided by, epsilon over 3 plus epsilon over 3. So just sum all those up. And this is equals to epsilon. Alright, so now we have this, and we'll tie this all together, but because we know that, well, but if we look right here, if you recall, so this one here, we're just assuming that it's true at the beginning. So if we have this right here, actually going back into the definition side right here, yeah. So basically, the limit will right here of the vector function r of t as t approaches a will equal to the vector b. So if we have this scenario for the precise definition, we need to show this. But first, what we'll show is that if we take, we're going to have this scenario. We'll have the vector function minus the b vector. And that's going to be less than the epsilon, so we always have this case as we make this smaller and smaller. Hence, that's how you can show that the limit exists. So now, this one right here, the magnitude or the difference between here, this is just the length of these difference of these vectors. In other words, this one is just using the Pythagorean theorem in 3-dimension, or just the distance formula in 3D. So we'll go over this right here, and I'll recap that later. So, but the difference right here. So I'll just write this as but r of t, the difference, the magnitude right here of the vector function r of t minus b vector. This equals 2. So, well, first of all, this equals 2. This is the difference right here. Before I get to that, this equals 2 in its component format. This is just equal to. Let's put the full length outside of it. In vector form, these are just subtract the 2. So in other words, this is just f of t minus b1. Like that. And then the middle component is g of t minus b2. And then the next one is h of t minus b3. And then we want a length of that. And then this all equals 2. This will just equal to the square root of, again, the absolute value of it is going to be the distance. This is going to be f of t minus b1. I'll put it like this, squared plus, and this is just, again, this is distance between difference of vectors there. This is just distance between those 2 points, essentially. This is going to be now g of t minus b2 squared plus h of t, I'll put the square bracket, h of t minus b3. Squared like that. Alright, so we have this, and what we also can do is, well, this is going to be less than or equal to, and it's going to be less than or equal to by, well, if we take these all together, and basically, look at these each separately. So instead of adding all these up, what we're going to do is just add up this one right here, take the square root plus this one, plus that, and then it's going to be less than or equal to it. Yeah, so this one right here is going to be less than or equal to, and we're just doing basically the maximum size we can do. So what I mean by that is it's the same thing as writing right here. This is square root f of t b1 like this squared. So we square root this like this, and then plus. So then this is going to be a positive value. Square plus this one. So then this difference is going to be, well, less than or equal to this one. This is, you're not going to get anything bigger than this one. This is going to be g of t minus b of t squared plus last one h of t minus b of 3 squared like that. Alright, and then going further, this equals to, well, now just separate these. Yeah, cancel the square roots and the squared. So then this is going to be right here. Put this, take the absolute value sign in this, because this is also positive there. So this is going to be absolute value sign f of t minus b1 plus absolute value of g of t, the difference, minus b2 plus h of t minus b3, like that. So that is what we have there. So in other words, this difference is equal to the summation of these differences. In other words, this right here, we already have these. We already solved this one right here. This is just from the component parts, and this is going to be less than epsilon. So this is we just solved the thingy. So less than epsilon. So if the limit exists, it needs to be the difference needs to be less than epsilon. And again, that's if this and this is where t minus a. The absolute value of t minus a is going to be between 0 and epsilon. So in other words, we literally just solved it. Yeah, so in other words, yeah, we solved it. So thus, for every epsilon greater than 0, there exists a delta greater than 0, such that we have, such that 0 less than, this is going to be t minus a delta. Or I'll actually put the if sign. So if there. So if 0 is, t minus a, the absolute value of that is going to be between greater than 0, less than epsilon, then what we have is, well, this is the difference between the vector function and the vector b is less than epsilon. I mean, less than less than right here. Yeah, so thus we have this, and then thus our initial one is true. Well, we assumed it was the vector existed, and now we prove that it does by the precise definition. So thus we'll just go back to here, limit as t approaches a. I just put this for completeness in one section. This right here exists. Equals to b vector. Yes, we just solve that. And I'm going to solve it a different way. And here I quickly just, actually before we get to the second solution, I'll just quickly change things up. So basically I wrote this here. So this proves our limit. And I'll just put the limit right here. Limit as t approaches a of the vector function r of t. This equals to b vector. Yes. So now let's continue further. And also one final note. Note that I used the distance formula in 3D for my earlier video, and that's for here right here. So distance between this is just basically the magnitude is just, or difference is the same as the distance between these two vectors. This is a vector function and then vector b. And I just used that for my earlier video. There's a link to it, and there's the thumbnail of it. And basically the distance between P1 to P2, you could same thing as writing it as if they're vectors, you could do the vector between them. But anyways, the magnitude or the distance is going to be equal to the square root of the difference of each component squared. So x2 squared, x2 minus x1 squared, and then so x2 minus x1, y2 minus y1, and then z2 minus z1 on all those squared, and then square root the whole thing. Right, so epic stuff. So now let's take a look at the do this solution to this again, but in a different format. Just the solutions manual had two different solutions, so we'll solve it using a slightly different method. And the first one we started off with assuming that the limit existed, and then showing that this is the case. But now we're going to go the reverse. We're going to start from here and then going all the way back up the other direction. So conversely, suppose for every epsilon greater than 0, there exists delta greater than 0 such that if, alright, we'll write if, and then we'll do the usual. So the interval, this is t minus a, the absolute value is between 0 and epsilon. So we're going to have, now the difference is going to be here. So suppose we have this scenario, and then we're going to go back and prove that it's actually the limit. This is the rt, this is the vector function minus the b. This is going to be less than epsilon, like that. All right, so now we have that, so then we'll go from here now. So thus, put that over here, thus, this is going to be now RT. Just take the difference from here. So now we're doing from this direction as opposed to, again, from solution 1 was the reverse direction. So minus B, put these in components. This equals 2, the same thing as difference. This is going to be f of t minus B1. All right, so it's B1, and g of t minus B2, and then h of t minus B3, and then absolute value sign. All right, and also, this is going to be less than epsilon, so move it over, less than epsilon. All right, so we have this now, and now what we'll do is again, apply the distance formula right here, so then do that over here with this. So then this is going to be the magnitude is equal to, put it like this, square root, and then put the whole thing in again. This is going to be, this is f of t minus b1 squared plus g of t minus b2 squared plus h of t minus b3 squared. And now this is going to be less than epsilon. So that's just the distance. Whoops. Let's extend this further, like that. And now what we'll do here is we're going to square both sides. So if we square this, what we end up having is, then this will cancel. If we square this, this will cancel. We're going to get this over here, and we're all going to, yeah, this is squared. Yeah. So what will end up happening is the square roots cancel. So if we just square this and then square this whole thing, etc. Yeah, so we'll just do that both sides. So what we get is this cancels. This will be like this: f of t minus b1 squared plus, like this, g of t minus b2 squared plus h of t minus b3, like this. And then this is squared. This is going to be now less than epsilon squared. All right, but each term on the left side of the above inequality is positive. So these are all positive because you have the square there, so it's always positive, positive, positive. So in other words, no single one of these is going to be greater than, no single one is going to be greater than epsilon squared, so because there is no negative ones. So in other words, every single one of these individually is going to be less than epsilon squared. So thus, what we're going to have is put these all together. So thus, if we have, and I'll put this starting from the beginning right here. So if this part right here, if 0 is t minus a, the interval is greater than 0 and less than epsilon, then here, and now we've essentially, we just squared these ones right here. So then what we'll do is I'll put this like this. The our vector function minus b, like this, and this is all squared. This is going to be less than epsilon squared. So that we get that, and we get every single one of these components. So we're going to get now this right here, f of, now let's fix this a bit better. This one right here, this is going to be f of t minus b1. Okay, because they're all positive, this is going to be less than epsilon squared. And then similarly, we're going to have g of t minus b2 squared is less than epsilon squared. And finally, we're going to have, this is going to be h now. H of t less than b3 squared. And I'll fix this up. Is less than epsilon squared. Here, I just shrunk those inside here, and and then we could just cancel all these squares though. So or we could just have f of t minus b1 is the absolute value because it's all positive there. So we just take the absolute value. It's less than epsilon. Yeah, so we just take square root of both sides and take the absolute value. This is going to be less than epsilon. We're going to have g of t minus b2 is less than epsilon, and finally, absolute value of this h of t minus b3 is less than epsilon. And these are just real valued functions, so these all have limits. Right, and by definition of real valued functions, we have, again, these are all just limits. In other words, if we have this scenario and then we have every one of these, then we just basically, the limit exists of each component. So thus, limit as t approaches, this is going to be a of f of t, this equals to b1. So that equals to b1. The next one is limit as t approaches a of g of t, this equals to b2, and then limit as t approaches a of h of t, this equals to b3. All right, and then by definition 1, by definition 1, this just means that we know that the limit as t approaches a of the vector function r of t, this equals to its components. Yes, in other words, this equals 2. This is going to be like this. This right here. Limit as t approaches a of f of t, and then limit as t approaches a of g of t. Again, just by limit of the vector function is the limit of its components by definition. Limit as t approaches a of h of t. Alright, so we have this. I think my calculus book uses actually a bigger bracket like that. But it's, yeah, I'll do the bigger brackets for now. Anyways, I've been doing the smaller ones before, but it's not a big deal. This is gonna now equal to, yeah, so this equals to, basically, this is gonna be, B1. Actually, I don't like these big brackets, I like the small one, it's pretty straightforward. I put bracket like that. Anyways, this is gonna equal to now, bracket B1, B2, because all these limits exist, B1, B2, B3. And this equals to, well, this equals to, I'll put it right, yeah, let's put it here. This equals to the B vector. So there it is. Or I'll put it like this. Limit t approaches a, yeah, of r of t equals to B vector. There it is. So we've proven the limit. So this is proving the limit from starting from the bottom of the definite or the bottom of the precise limit format. So we started. The first solution was you solve it from. We were assumed this is true, and then we show that this is the case. And then the second one, solution 2, is we started off from here. We have this if and only if every epsilon and delta and so on. We get this, and then we show that going backwards is here. So yes, epic stuff there. All right, and now we'll go over here. The next part of that same exercise is visualizing the precise definition of a vector function limit. This is actually my own undertaking. This wasn't in the solution manual, but I thought it's pretty useful to do. So we can visualize the definition in 3D, definition, or just a precise, I'll just say precise definition of the limits in just the same way as we did in 2D. So if we recall from my earlier video, and here's screenshots from the calculus book. So basically, this is the visualizing the precise definition in real valued functions. This is in 2D. And then in the vector functions setup, we need to do that in 3D. Well, we're doing it in 3D and in vector form. So what this means is, and I'm going to do this actually half, I'm going to do this all like pretty much on the go right here. I haven't done this one. I did it before, but I think I did it a bit wrong. I'm going to draw X, Y right here. This is Y. So we're going to do this all improv right here. Yeah, that's the word I was looking for. Like here. So let's say we have this. All right, here I'm going to draw in red the vector. This is the vector B. So let's say we have vector B like this. This is B. And I'll put this right here. B vector. And this has components. B vector equals B1, B2, B3. And what I'll do is since it's already in red, I can just move this away. Okay, so it's going to look something like this. This is how it should be. And then I'm going to draw in, we'll draw it in black, the R vector. So this is going to be now, let's say we have an R vector that goes somewhere here. This is our R vector. Oh, this is our vector function, R of t. This equals to, yeah, let's put that, it's R vector. This equals to f of t. This is a vector function, g of t and h of t, like that. And now what I'm going to do is I'm going to draw a sphere. Let's say this was the farthest away at it was from this point. At this point is the farthest away that the R vector our vector function is from the B value. I'm going to draw this in blue. And what we end up having is a sphere. So we literally have a sphere where, and again, this is a parameter. So this is going to be right here. This is this parameter is between 0 and this is the absolute value of t minus a, like that. And this is going to be, and it's going to be between epsilon, like that. So that's, 0 is between, t minus a, the absolute value is going to be between 0 and epsilon. And since it's a parameter, it's not going to be anywhere on the xy axis. It's its own variable that this vector function is dependent on. So then what we're going to do is so we have that point there, and also I'm going to draw the a value. So everything that's in this one here, the a is all the way across here. No, actually, that would be wrong. Okay, so the a is not there because again, a is part of the parameter t, but the center point is basically where the t value is. This is when t is equal to a. Yeah, so when t is equal to a, that's when we have it at this exact center point right here. All right, so that's what would be the t equals a there. I'll put it right here. This is at t equals a. So that is at t equals a, but again, that is, I'll just assume it's a, I'll just put a circle there. And then this is going to be at t equals a. Yeah, so that's the a there. All right, so that's the t equals a, but then this whole thing is in between it, and I'm going to draw this and highlight it now. Yes, I'm going to, actually, before we highlight it, yeah, so this is going to be like a sphere. Yeah, I'll draw it like highlighted. So the whole thing is highlighted in 3D. Alright, here I just pause video and just highlight it, fixed it up. And I didn't highlight over this red just because it turns it into black. So anyways, we have that. Like that. Alright. Yeah, so if that's the epsilon, then if that's the delta, then the epsilon is going to be the distance between here and here. This is going to be epsilon like that. Alright, and then finally what we'll end up having is, so I'm going to draw this in red now. So I move these over closer. So again, bear with me, this is going to put it down right here. So if we put this all the way down, all the way across here, we're going to get a now component. This is going to be, I'll put this as, this is going to be our B2. This is, B1, that's B1. And then this right here is going to be on all the way across here. This is B2. This is B2. And then likewise for the Y is going to, the vertical component has one as well. So the vertical component is going to be, yes, I'll just draw the vertical component. It's going to go across like this, dot, 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 dot. And this is going to be like that. This is going to be B3. And then, whereas this part right here at the bottom, I'll draw this in black. So this is going to be right here. This is the R. Let's draw it around like that. So it's going to be somewhere around like this. So this is the R, and then it has the G, F, G, and H. But what I'm interested in is over here. So this distance right here, this is going to be our, we'll call this as epsilon 1. And then the Y is going to be all the way across here. This is epsilon 2. And then likewise, the bottom is going to be all the way across here. I'm going to draw this dot, 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 dot all the way across. And then the difference here is going to be, well, epsilon 3. So again, that's the component parts of it. So I just wanted to put that in there as a visual demonstration. Like that. Alright, so that is that. And I'm just going to keep it like that, otherwise it's going to get more and more messy. And now, and then as you shrink this interval between t minus a, as it gets closer and closer to a, this gets closer and closer, this gets 0, smaller and smaller. And then that interval, and this one gets closer and closer. So that's basically the limit as this is approaching closer and closer to this part right here. And I wanted to do this in 3D, just basically get a sphere-like setup there. This is the maximum value there. Yeah, this is the maximum, this is the epsilon is the maximum setup there. And in between it, where this was the interval right here, and this would be the highest point, highest t value that gets this epsilon, or gets close to it. But anyway, that's the maximum, and this number gets smaller and smaller, again, always greater than 0. Yeah, so this means that as we shrink, again, I just wrote it down, as we shrink the interval of the parameter t, by picking a smaller delta right here, so yeah, as you get smaller and smaller towards there, because again, depending on the value of t, as it gets closer to a, but the main one is this interval right here. This parameter, this delta right here. So by picking a smaller delta, so if we can keep getting this super small, if there's always going to be a t value such that then yeah, it's such that the difference between here gets smaller and smaller if the limit then basically this is approaching that vector. Then the difference between r and b gets smaller. In other words, epsilon gets smaller, and we can keep doing this indefinitely. In other words, the limit exists and it becomes this vector. So all these approach these numbers right there. All right, epic stuff. All right, and now let's take a look at exercise 2 finally. All right, so suppose u and v are vector functions that possess limits at as t approaches a, and let c be a constant. So we're asked to prove these properties and basically just show that they're the same thing as for regular limits. So prove the following properties. So if you have the limit as t approaches a of this right here, this addition or subtraction, so u of t plus v of t vector functions, this just equals to the limit as t approaches a of the u t vector, u of the u vector function plus the limit of the as t approaches a of the v vector. So basically, if you add the vector functions and then take the limit, is the same as doing the limits of them separately and then adding them up. And then in part B is limit as t approaches a of, now we have the constant times the vector function, and with this one we can just take the constant out. And then part C is the dot product of the vector functions. The limit is the same as doing the limit of them individually and then taking the dot product. And same with the cross product for part D. The limit of the cross product is the same as the limit of each vector function multiplied by the a cross product with the other limit of the vector function. All right, so let's take a look at the solution. But before we get to each part, what I'm going to do here is basically I'm going to define the term. So I'm going to go let u, so u vector function, and then define each of these component parts. I'm going to go as u1 of t. So this one has component parts and it's in 3D. u2 of t, and then u3 of t, like that. That's the component parts of this one. And then likewise for v of t, this equals to v1 of t, v2 of t, and then v3 of t, like that. All right, and basically we define these, and then basically the next setup is, I'm gonna fix this up a bit, move this right here. Yeah, I'll just move this right here. All right, a bit higher. All right, so in each part of this problem, the basic procedure is to use definition 1. Basically, the limit of a vector function equals to the limit of its component parts, and then analyze the individual component functions using the limit properties we have already developed for real valued functions. So let's take a look at the solution to A. So A is this one right here, addition or subtraction. The same thing would follow, but we'll just do with the addition because this was part of the exercise. So we're gonna take this part right here, and I'm gonna go reverse. I'm gonna. Oops, I was erasing it. So what we'll do is take this and then reverse it to go backwards. All right, and doing the component parts and so on. So expand them out. So let's take that right here. So I'm going to go limit as t approaches a of u vector function plus limit as t approaches a of v vector function. This right here, this equals to, this equals to the limit as t approaches a of, now we do the component parts of every single one, and we should put this inside. I'll move this over. So this is the same thing as the limit of each one separately. This is just definition 1. This is going to be now, this is f of, u1 of t. And then limit as t approaches a of u2 of t. And then limit t approaches a of u3 of t. And this is going to be like that. And already here I just quickly shrunk that in, and then that's the u1. Now we have to plus the v1. I'll try to write it a bit smaller. Limit as t approaches a of that's inside of it. So this is going to be limit t approaches a v1 of t, and then limit. So again, it's just very tedious, but straightforward. You just put using the definition definition 1, and put this all inside. And this is t approaches a of, this is v3. And we know the limits of these component functions must exist since the vector functions both possess limits as t approaches a, i.e. if the limits of the vector functions exist, then so does their component function. That's definition 1, where the limit of this, basically the limit of this one, again, that's definition 1. If these limits exist, the components have to exist. And also from again here. So we're told that, suppose u that possess limits as t approaches a, so they both exist, and then if you add them up, so add them up would also exist and so on. But I mean, the component parts have to exist because they exist. Anyways, then adding the two vectors and using the addition property of limits for real valued functions, we have, so what we get is, just put this down again, limit as t approaches a of u of t plus limit as t approaches a of v of t vector function. Okay. This is going to equal to now, and now we could sum all these up. This one here, we just sum up the component parts, so limit as t approaches a, and then this is going to be u1, and this plus this one right here. So again, these are just basic limit properties now, because these are real valued functions, so we can add these up. Limit, and this is just, just the basic functions right here. Limit as t approaches a of u1 of t. Actually, no, these aren't real valued yet, but nonetheless, these are, actually, they are. This will equal a, because it's not a vector function anymore. This is just a real function, and then that equals a limit, so that we can just add up those limits. Same thing as adding them up. And then this is going to be of each component, so the limit as t approaches a of, this is u of t2 of t, and then the next one. And I want to fit these all in one line, so what I'm going to do is, I'm going to write this down here. So that equals 2, and I'll move it all the way across here. Let's see if I could fit everything into one line, otherwise I'll have to shrink it. This limit t approaches a of u2 of t plus limit, I'll make this a bit bigger, limit t approaches a of u, v, 2 of t, and finally, let's move this all the way here, limit as t approaches a of u3 of t plus limit as t approaches a of v3 of t. And then put a close bracket. Alright, here, and I quickly just shrunk this in to fit one line right here. Alright, so we shrunk that in. So now this equals 2, and I think what we could do next is, well, this limits right here, these two limits are the same thing, so we just add these up, and this is a v2, not u2. So it's v2, v1, not the other one. That's u1 of t plus limit v1 of t. So that's what it is, and then all these line up. And then what we could do is we could take the limit out and then sum these up separately. So we could take the limit like this, and this becomes a u1 of t, so separately like that, plus v1 of t, like that. And then next part is limit, and this is going to be u2 of t, plus v2 of t. So just, again, the both limits are the same, so we just basic limit properties, so just take that out. And then next one is limit t approaches a, and this is going to be u3 of t plus v, erase this. Alright, and add a plus v3 t, and then close that up and see if it fits in. Yeah, it fits in our line. Actually, we need one more bracket. And that fits in our line like that. Let's see if it fits in. Yeah, fits in close. We have some room. We'll make it neater. All right, so that should be exactly there. Yeah, so we have that. And all right, so we have this, but this is just definition 1 on the right side. So in other words, the limit of each component part, we could just go backwards and get back into the limit of these separately. So in other words, yeah, I mean the limit of the vector functions added together. So then this just equals to, yeah, I'll put this right here. Yes, in other words, we could take these limit out, again, just going reverse from the definition 1. This just equals to limit. We could take that whole limit out. Same thing. So limit of the component parts, same thing as limit of the total. And this is going to be now, this is going to be of the vector u1, u2, v2, like that. Oh, this is v1. I keep getting that mixed up. U2t plus v2 of t, and then u, and then like this, erase this, u3 of t plus v3 of t, like that. So that's what we have there. And again, I'll put this right here, write this down as, right, fix this t there. And this is, I'll just put this right here, using definition 1. 1 backwards. So that's how we got to it. That's how we got it. And again, this whole setup is, well, this is just the limit of this right here. And this is just a vector of the vector functions added together. U1 of the component parts added together. So then this just equals to limit as t approaches a of the vector functions added together. ut plus v of t, like that. Epic stuff there. So that is what we get. That is, we just proved it. So we just proved it. Go back to a, and there is a right here. So we went from here all the way back to there. So now let's take a look at part B. And this one, now we have the constant right here, and then we could take it out. So we'll start off with, in this case, we'll start off with this one right here, and then go backwards to that one. All right. All right. So let's, jump right into solution B. So we'll do that. So we're going to write this as limit as t approaches a of c times by u of t, like that. Now this equals to, again, by definition 1, put these all in the component parts together. So this is going to be equal to, actually before we even get to the component parts, I'm just going to write this out as limit as t approaches a of, put these all in, just in the components c1, we don't put the limits in right now, c1 u of u t, this is again by definition what this means, c u t, and then c u t3, u3 now, and then close this all like that, and yes, that's what we have. And we will put this all together into one. So that's equals like that. But we could take we'll just take the limit of each component part. So it's the same thing. This is going to be limit as. So just for completeness, put that all together. So now it's going to be like this. cu1 of t, and then limit as t approaches a. And this one's pretty straightforward. All right. And this is going to be cu2 of t, and then limit t approaches a, like that, cu3 of t, like that. All right, and then for completeness, let's write this all out. Now we just have a basic limit right here, a limit of a function, and then we can take the c out of the limit. Again, we already covered this before. This just equals to, again, for completeness, put them all together in there. This just equals to, right here. Yeah, so put them in each one. So take the c out, limit t approaches a, and this is of u1 of t. Try to power through, and this is going to be c limit t approaches a, u2 of t, and then c u3. Oops, before we do that, limit, and this is going to be this is going to be u3 like that. And again, now this is just a constant inside of a vector. The components, we take the c out, and now the c is going to be out of it like that. Limit t approaches a of u1 of t. Limit t approaches a of u2 of t. Limit as t approaches a of u3 of t. Like that. So that's what we have. Alright. And then finally, we can go from here to reverse direction of the definition. 1, so this limit of a components, that's just the same thing as limit of the full vector function. Or we take that out first. So this is equals to c times it by limit as t approaches a of, right here, this is going to be u1 of t, u2 of t, u3 of t. Alright. So that's what we have. And in other words, this right here is just a vector, the u vector function. So this is going to be limit t approaches a of the u vector function, like that. And I'll just box this in like that. Alright, and that is exactly what we have. Yeah, so that's what we have, and we can see that from the value right here. So there's the b. So limit as so we went from here, and we got all the way over to here. So we took the constant out, just using basic limit laws and definition of the vector function limit. Alright, and now let's take a look at part C, and this one says limit as t approaches a of right here u of t dot product with v. And that equals to the limit of each vector function dot product with each other separately. So we take the limit and then take the dot product. It's equal to the same thing as taking the dot product and then taking the limit. All right. So what we'll do here is we'll start off from here in this solution, then we'll reverse like that. Again, that's a solutions manual had it, but again, pretty straightforward stuff there. So let's go to solution to C. So what we'll write is the limit as t approaches a of u of t dot product with v limit as t approaches a of v of t. This equals 2, and this equals 2, and I'll put it down here because we're going to need a lot of space. So this is going to be equal to, and now we take this and put the limits inside of each component part. So in other words, it's the same thing as writing limit as t approaches a of its component parts u1 of t, limit t approaches a of u2 of t, then limit t approaches a of u3 of t, and then dot product with, so we need to do dot product with it all, or it is pretty extensive, so I'll keep doing it here, and I'll just shrink it. It's going to be dot product with limit as t approaches a of u, this is v now, v1 of t. This is going to be now limit t of a like that. Yeah, t approaches a of v2 of t. Finally we have limit as t approaches a of v3 of t. Like that. Like this. Alright, so now we have that, and now we can take the dot product, and dot product as well, you just multiply each component and then add them up. So multiply this by this, add up with this one times by this one. So in other words, we get something like this. Yeah, here I just shrunk it up to put it in here, so we're going to get a limit as t approaches a, times it by u1 of t, and then times it by, this is going to be a multiplication, so put it like that. This will be a limit t approaches a of u1. This is v1 now. So we multiply this one with this. With this one, this and this, multiply it by each other, and then the other one, and so on. So we just do that each one, and then add them up. This is just a dot product, if we recall from my earlier video. So this is, you should have it ingrained in your head by now, if you followed me this far. This is going to be limit as t approaches a of u2 of t. And then this is going to be limit. Oops. Let's fix that up. Limit as t approaches a of v2 of t. And then plus last one, so one more, is limit as t approaches a of u3 of t multiplied by, fix this bracket, limit as t approaches a of v3 of t. Alright, so we have this. Yeah, we have this now, and now we can simplify, do some simplifications. So this is, we have this limit right here, and then times it by this one. Well, that's just the multiplication. We could take the limit out of these separately. So this equals to limit as t approaches a of, now, this one could be separate. This is just u1 of t times it by v1 of t. Alright, and then this again, basic limit laws. Now we can take the limit out of the this one in the middle, because they're the same limits as t approaches a. So we could do that as well. This is going to be u2 of t, and then v, and then v2 of t, and then plus limit t approaches a, and now it's going to be a u3 of t, v3 of t, like that. Alright, fix this t up. Alright, and then what ends up happening here is, well, this is a straightforward, take another one. This is another limit law of addition. We just take all the limits out. So limit as t approaches a, and now what we end up having is a big giant u1 of t, v1 of t, plus u2 of t, v2 of t, plus limit as this goes to, yeah, I mean, there's no, we already took the limit out, u3 of t, v3 of t, like that. In other words, this right here, this just equals to, yeah, this just equals to the limit as t approaches a, and it's just a dot product of the, yeah, this is just dot product of each one separately. Yeah, this is just u vector function dot product. Yeah, you take a dot product of these two vectors, vector functions, and then take the limit. So same thing. Yeah. So this is correct, and we can yeah, go look at it above here. So there is the limit right here. So we went from here and showed that, yeah, the limit of each vector function and then dot product is the same as taking the dot product first and then a limit. All right, now let's take a look at part D, and this one is now we do the same thing for the cross product. So the limit of the cross product, you do the cross product, then take the limit, is the same as doing the limit of each vector function u and v, and then taking the dot product. And yeah, and this one also we're gonna go from in this part D, we're gonna go from here and then go backwards and show it again using just a basic definition and limit laws and so on. All right, so let's jump right into part D for the cross product. All right, so let's take a look at the solution part D. I'm gonna write down now we have the limit, so we're gonna take it from the right side first. So basically write it like this: limit as u a vector function of t, cross product with the limit of t approaches a, and now this is v vector function, like this. And a good way to memorize the cross product is again using the the method where you just draw it in the determinate form or in the matrix form. So what we'll do is this same thing as writing limit. I like writing it like this, and this is going to be u 1 of t, and this is going to be our I vector, like that, and this is going to be like this, and then the next one is, this is the bottom one is the v vector, v1 vector of t, And then this is going to be our j. And this is going to be limit t approaches a of u of 2 of t. And this is, and yeah, remove these vector signs. These are components of the vector function. So those are bytes. Those are just regular functions. And then this is going to be the bottom limit t approaches a of v2 of t. And then the k component right here. It's going to be the limit as t approaches a of u3 of t. And then this is going to be limit as t approaches a of v3 of t. I just put it like that just so it's easier to memorize how to do the cross product. Alright, so now we have this. Now we could take our, do the cross product, and then if we recall how we do it, just cross this out, and basically cross this out, and then basically have this one multiplied by this, and subtracted by this multiplication. Alright, so I'll erase this. So let's see if we could, how many lines we could fit this in. Hopefully we can try to shrink it. So this is going to equal to, like this, this equals to, and this is going to be the, I'll put it in this bracket form. And instead of writing ijk, I'll just leave it like that. So it's going to be u limit as, and this is going to be multiplied like this, t a u2 multiplied by, this is going to be limit as t approaches a of v3, and then minus, this is going to be limit of u3 of t approaches a of u3 times it by, put this there so that we're not dot parting, we're just multiplying. This is going to be limit. This is going to be limit as t approaches a of this is, and also yeah, we can't dot product because it's not a vector. These are just functions right here. This is going to be v2. So this one. So this times by we're going to subtract this times this, and this is going to be v2 like that. And then we put a comma for the next setup. So that's comma, and now we do the next one. Is going to be like this. Yes, if we recall, we do it. So now we cross out this one right here, and then the bottom one's going to be a minus. So instead of having this multiplied by this, then subtract by the other one, we're going to instead have, because it's be a minus. I'll just do it because we don't have much space. I'll do it this way here. This one multiplied by this, and then subtract, because the middle one's the only one that has a negative one. So we do the opposite side. So what we'll do is, this is going to be limit, put in a bracket, limit as t approaches a of u3 times it by limit as t approaches a of v1, and then minus limit t approaches a of u1, and then limit times it by t approaches a of v3, like that, and then comma. All right, then comma, and then the last one, just do it the same as the first one. So we erase this, cross this out. So now we multiply these two together, subtracted by this one over there. All right. So let's erase these. All right, and also cross this out. All right, so we get the idea and cross this out. Okay, so this is going to equal 2. Or this, the next part is going to be, and again, that's going to be u1 v2. So limit t approaches a of u1 of t, and then limit as t approaches a of v2 of t, and then the other one's the reverse direction, minus limit t approaches a of, now it's going to be the u2. So reverse direction, instead of u1, it goes u2. And then goes to limit, instead of v2, goes v1. And then this is going to be v1 of t. And close bracket. There it is. That's the closed triangle bracket there. Alright, so now we have this, and now the next setup is just again using basic limit laws for functions. So we can take the limit out of this multiplication and also the subtraction. So we just do that all in one go. Yeah, so what we end up getting is this equals to limit. Actually, each one separately. So we're going to do a like this. This is going to be equal to, put it like this, limit as t approaches a of, now this is going to be u2 v3. u2 of t, v3 of t, and then subtracted by this one right here, u3 v2. u3, and again, you can see this, if this is u2, and that's v3, the next one's going to be u3, and the other one's v2. So it's always just reverse. Alright. So that's this one here, and I'm going to move this over. Right here, just so it's all in one line. I mean, 2 lines. We don't need to go 1 line. This equals like this, and then put a comma, and the next one's gonna be limit t approaches a of, now this is gonna be, this middle one is gonna be u3 v1, and then u1 v3. So u3 limit t approaches a. Actually, no, we already got, my bad, we already got rid of this limit right here. Alright, so we already got rid of that. So this is going to be just, yeah, that's just going to be right here. u3 v1, and then u1 v3. So u3, okay, u3 of t, v1 of t, minus, and then this is going to be u1 of t, v3 of t, like that. And then that last one is going to be, where's my eraser? There it is. And last one's going to be limit as t approaches a, and this is going to be, yeah, u1 v2. So u1 of t, v2 of t, and then the reverse direction, u2 of t, v1 of t, like that. And yeah, this is a close bracket for close this. And then this is close bracket. There it is. That's what we have there. And now what we have these are the limits of the components, and then we go reverse on the definition. One, in other words, this is the same thing as writing limit of the full vector of function, not just the components. So this equals to limit t approaches a of the full setup here. Yeah, and now this is just going to be u2 of t, v3 of t, minus u3 of t, v2 of t, and then comma, the next setup is going to be u3 t, v1 of t, minus, and see if I can fit this all in. Yeah, so I will write this all in and then shrink it or shift it. And then this is going to be u1 of t, v2 of t, minus u2 of t, v1 of t, and then close bracket like that. Alright, so here I just moved it in and shrunk it so it all fits one line. And that is, yeah, let's double check my solutions manual. Yeah, this is exactly, yeah, this is the cross product of, and then this just equals to, well, this whole thing just equals to the limit. This is a cross product. Limit as t approaches a of the cross product. ut of cross v. Alright, so there it is. And that's exactly what we have there. And yeah, we can just scroll back up to the question, and we could see, yeah, so we basically, we went from here, we showed that the limit of the individual vector functions, then the cross product equals the same thing as if you take the cross product and then take the limit. So yes, epic stuff there. Alright, and now let's take a look at exercise 3, and this is on the trefoil knot, or trefoil knot. I'm not sure exactly how to pronounce it, but I will call it trefoil knot. So the view of the trefoil knot shown earlier and copied below, so I copied it here from my earlier video, is accurate, but it doesn't reveal the whole story. So here's the parametric equations of it, and it looks like this. So yes, this is a bit next level. It's hard to tell exactly how it looks or behaves from like different angles and so on, so we'll have to look at that. Alright, yeah, so this is a trefoil knot. So we're asked to use the following parametric equations to sketch the curve by hand as viewed from above, with gaps indicating where the curve passes over itself. And yeah, and here, that's another part from this angle right here. We don't know which one goes above, which one's below. Is this behind it? Is this in front of it? And so on. So here's the parametric equations. These are the same ones. Here I just copied from the earlier section, but now here's from the actual exercise. So x equals to 2 plus cosine 1.5t, all multiplied by cosine t. And then y is equal to 2 plus cosine 1.5t, and then all of that multiplied by sine t. And z is equal to sine 1.5t. And we're asked to do this. So start by showing that the projection of the curve onto the xy plane, so basically for the vertical projection straight down to the horizontal, has polar coordinates r equals to 2 plus cosine 1.5t, and theta is equal to t. So yeah, and this is polar coordinates. So r varies between 1 and 3. And that's because right here, if this is the polar equations, r equals 2 plus cosine 1.5t. Cosine is always going to be between 1 and 1 and negative 1 as the minimum and maximum. So it's going to be between 2 plus plus 1, which is 3, or 2 minus 1, which is 1. All right, then we're asked to show that the z has maximum and minimum values when the projection is halfway between r and r equals 1 and r equals 3. So it's somewhere t in between those. When you have finished your sketch, use a computer to draw the curve with viewpoint directly above and compare with our sketch. So basically, we're asked to sketch by hand the vertical projection onto the xy plane, and then compare that with a computer. Then use a computer to draw the curve from several other viewpoints, and we're given a hint here. You can get a better impression of the curve if you plot a tube with radius 0.2 around the curve. Use the tube plot command in Maple, or tube curve or tube command in Mathematica. These are some mathematical programs, pretty advanced. I think you have to like download and so on, but I'll just use GeoGebra and work around it as I can. All right. So anyways, let's take a look at the solution. So the projection of the curve onto the xy plane is given by the parametric equations, and we just take the x and y components, and then we just set z is equal to 0. So if we set this equal to 0, then that's just going to be the graph right on it. So I'll put that for completeness. Yeah, for completeness, I'll just add this here. The solution panel didn't include it, but I like including it. This equals 0, like that. Alright, and now we can convert these polar, or these equations right here, these parametric equations, to polar coordinates by finding the distance from the origins. If we recall from my earlier video, again, polar coordinates are pretty straightforward. So if I'll draw this xy axis, so we're just doing it in 2D, like this. So if we have this right here, this is the x, this is the y right here, and then, so to get polar ones, if we have the point right here, this is on this point right here is going to be, so basically if we draw this like here, so polar ones, we just convert it from a, I'm going to put this all the way there. Yeah, just fix that up. Yeah, so if we have this point right there, and I'm going to call from, this is the, I'm going to call this distance r. So this is the distance from the origin. I'm going to draw this angle right here. I'm going to call this theta, and I'm going to set this equal to t, and we'll show that it actually is t, and basically, because again, we're converting it into polar coordinates. So if we draw it like this, this is the top side. So this is the y. This would be the y component, and this is our x, y point. So the y is going to be equal to our parametric equation, 2 plus cosine 1.5t, and then times it by sine of t, like that. And then this is the x, and then this x is equal to this equals to 2 plus cosine 1.5 t times by cosine t. And again, this is the origin. So put a O there or 0. So now by the Pythagorean theorem, Pythagorean. Alright, here I just wrote that, yeah, Pythagorean theorem. So we're going to have r squared is equal to, well, x squared plus y squared. So the square of the sides of a right angle triangle is equal to the hypotenuse squared. So we have r squared equals x squared plus y squared. So now this equals to, plug in the x. X is going to be 2 plus cosine 1.5t. I'm going to square this, and cosine is going to be squared. Alright, here I just shifted it over, try to fit this all in one line. So now I was going to have the next one is going to be the y. The y squared is going to be, well, 2 plus cosine 1.5t, and then sine, and this is squared, sine squared t. So we have this, and we could take out the common factor right here. This is just the same one, so we could factor that out. So this equals to 2 plus cosine 1.5t squared. Factor that out. Now we're going to have so factor out, we're going to have cosine t, cosine squared t plus sine squared of t, like that. And now this is a Pythagorean identity. This just equals to 1. So that all vanishes. So what we're left with is, I'll move this over here. We're left with is r squared is equal to, and now we have 2 plus cosine 1.5 t all squared. Now we can just square both sides. We get a, well, what we're going to end up having is an r equals to, well, plus or minus, but we're only just going to look at the plus side because it's distance. So it's going to be plus or minus, and now we're going to have 2 plus cosine 1.5t, like that. And we'll only take the positive. I'll also put plus or minus because it's very interesting. I always get 2. But anyways, so we take the plus because we just want the distance from it. So this equals to 2 plus cosine 1.5t. So that is our polar equation. And this is in terms of t, but then again, t is just going to be theta, and we could show this, and we can show this by basically saying also note, I'll put this not caps lock. Yeah, also note, if we take right here, so I'm going to do tan of theta. So tan of theta there. Tan of theta is going to be, also note tan of theta. This equals to, well, it's going to be the y over the x. So this is a opposite over adjacent. So that's going to be y over x from the graph. So that's our theta. So y divided by x. And if y and x are the parametric equations, this equals to, well, the y is going to be, and I'll move this down. I'll move this down right here, so I have some room to operate. So, yeah, this is going to be 2 plus cosine 1.5t, and then this is going to be sine. The y has the sine. So remember the y has the sine, and then the x has the cosine. So divide this all by 2 plus cosine again, 1.5t, and this is going to be cosine t. So then this just cancels out. And yeah, if that cancels out, we're left with is, well, this just equals to sine. Yeah, this just equals to sine over t. Yeah, sine t over cosine t. And again, that's by definition just tan t. So again, that's opposite over adjacent. Opposite over hypotenuse divided by adjacent over hypotenuse. Hypotenuse cancels. And we'll do that actually for completeness, just so we can prove it all in one go, as opposed to just telling it's that. What I'll do is put it there. I'll cross this out. And this equals to, well, this is opposite over hypotenuse, and the hypotenuse is r. So again, the hypotenuse is just r, so we go y over r. This equals to y over r divided by x over r, adjacent over hypotenuse. So then r's cancel, we just get y over x. So in other words, this equals to, yeah, well, this equals to tan theta, but again, this is, again, tan of t as well. So this is, yeah, we could just erase this. Again, that was just a double check there. But again, this just equals to tan. Again, let's just show you the same thing. So this equals to tan t. So in other words, what we have is theta. So tan of theta is equal to tan of t, because that's just, again, definition slash just using basic trigonometry. So thus, what we get is right here, or yeah, this is what we get is theta is equal to t. Yeah, so we could just replace theta with t. Again, that was just an extra double check that it's all everything matches up. Anyways, so thus our parametric equation is, our polar equation for the parametric equations are r equals to 2 plus cosine 1.5 theta. So again, just for completeness, just put theta instead of t. Just so indicate it's an angle, and again, the same thing. And yeah, I'm not even sure you even need this, because it's just my calculus book stated that, but again, it's pretty straightforward. Theta is equal to t, because you just set it to it, you're just converting it into polar coordinates, and it's always going to be just when you're graphing it like that. Alright, and now we're going to start graphing stuff. So at theta equals to 0, so let's just start from the beginning as the parameter t or theta is equal to 0. We have r equals 3, and r decreases to 1 as theta increases to 2 pi over 3. And we can show this, well, basically at this is a 1.5 theta, and again, because that's it's that, so at 1.5 theta, this just equals to 3 over 2 theta. When this whole thing is equal to 0, then cosine of that is just 1. Then what we'll get is a r equals to 2 plus cosine 0, that just equals to, well, 2 plus 1 equals to 3. So that is at the beginning. And we can show this. I'm just going to recall. I'm going to draw a bunch of stuff here. So recall we will use this for throughout this setup here. So I'm going to recall the graph of cosine. I'm going to go this super far. And this is going to be theta. And this is going to be cosine theta. Let's put it like this, cosine theta. So we have cosine theta. And I'm going to go all the way up to 6 pi, because we will use 6 pi. I'm going to go, if this is 2 pi, this is 4 pi, then this is going to be 6 pi. So, and this is at 1. So that's at 1. Now we need to extend this one. Extend it all the way down to -1. Just so we grasp this all. And then this is in between, this is a pi. So it goes like this. And then it goes like, and it has to go all the way back up. So that it doesn't go like that. Yeah, if we recall, this has to go all the way back up to here. So it needs to, so then this would be the minimum there. So it's going to go like this. And then it goes like that. And same thing here would be at, this is pi, 2 pi, this is 3 pi. And it needs to go all the way down, and then go all the way back up. So all the way down, and this is a 5 pi. And we're just going to graph it for all these specific points. Or, yeah, just get the values there. So this needs to go all the way to the bottom. And I'm trying to draw it neat. Alright, it goes like that. And then goes up like that. Goes up. And there it is. Yeah, I'll fix it up. Alright, so here I fixed that up. And now the next one is, this is, so it starts off at 3 and it decreases to 1 as theta increases to 2 pi over 3. And in this case here, so when 1.5 theta is equal to 3, well, just equals to 3 over 2. This is 1.5 is 3 over 2 theta. Again, this is just, well, theta is equal to 0. So that's at theta is equal to 0 as our parameter, our polar coordinate parameter now. And then theta goes to 2 pi over 3, and we can see that, well, we'll just set it as, we go all the way to this -1. So it goes from the peak 1 all the way to the minimum -1. So at 3 over 2 theta is equal to pi, what we get is, well, what happens here is the theta, we'll just move this over there. So then this means theta is equal to, move the 2 over there, and then the 3 at the bottom, and so on. So we're going to get 2 over 3 pi. So 2 over 3 pi like that. And hence why we have this part right here. I wrote that there, 2 pi over 3. So then r is going to be now r is equal to 2 plus cosine of this right here, cosine pi, because we set the whole thing to pi, like that. And now this equals to, well, this is -1, so 2 minus 1 equals to 1. Yeah, so it basically goes from at the theta is equal to 0, it's at maximum 3, and it goes down until r is equal to 1 at theta is equal to 2 pi over 3. So there it is. All right, now going further, so we have the 2 points right here. So it starts at 3, decreases to 1, and I'll go another pi. So for 2 pi over 3, for theta is greater than or equal to 2 pi over 3, and all the way to 4 pi over 3, r increases to r again. So it's going to increase again. So when here you're going to increase to 1 again, then r is going to decrease to I mean it increases to 3 again, then it decreases to 1, increases to 3, decreases to 1, increases to 3, because again we're dealing with sine wave. A cosine just goes up and down. So and then r decreases to 1 at theta is equal to 2 pi, and increases to r equals to increases to 3 at theta equals to 8 pi over 3, decreases to 1 at theta equals to 10 pi over 3, and completes the closed curve by increasing to 3 at pi equals 4. So it's 2 loops, but this 6 pi is dealing with this is the recall there, but this is actually dealing with 1.5 theta. So for completeness, just so we don't get confused, I'm going to put this like this. This is at again, this is 3.5 theta. 3 over actually, I'm just gonna because it's pretty straightforward. This is just for cosine, but we're dealing with that. So I'm gonna put this in circle. So we're not actually using. We're not going to be using these variables. Are not associated with these in any way. I just have those for basic cosine. But now we're replacing theta with 3 over 2 theta, or 1.5 theta. All right. So basically for 2 pi over 3, and I'm just going to show you how all these. This is for my calculus book solutions manual, and I'll show you how this is all correct. And they basically go every pi. So the next one is so the next one is 4 pi over 3. But to get that, what they actually do is at 3 over 2 theta, when that equals to 2 pi. So it's going to increase again. And in other words, we can solve for this one. Theta is equal to 4 pi. Move the 2 over to the other side, 4 pi over 3. Hence why you get this number, what they get that. And then what we end up having is r is equal to 2 plus cosine 2 pi. Yeah, cosine 2 pi, which equals to 2 plus, 1. So we know here, this is just 1. So there it is. That's 2 pi. And you can see the idea. I'm just going to, for completeness, I'm just going to go over all of them. This equals to 3. Like that. So it increases there. And then the next one is at 3 over 2 theta is equal to 3 pi. Then we're going to graph these all later. So then the theta is going to be, 3's cancel. Then move the 2 over to the other side. This is going to be 2 pi. And again, that's hence why we get this one here. So it's going to decrease. And this is at this segment, so we're going to subtract by 1. All right. So you get the pattern there. So r is equal to 2 minus, this is going to be plus cosine 3 pi equals 2. Let's erase this. Now let's erase it. This equals to 2. Okay, things messing up. Okay, 2 minus 1. This equals to 1. So hence, at theta is equal to 2 pi. It decreases to 1 at theta equals 2 pi. So that's what we have. Now the next one increases to 3 at theta equals to 8 pi over 3. And you can see the pattern. We just add another. This one is if this was 6. Yeah, we add 2 pi each time to this top part. 2 pi over 3. I mean. So the next one is going to be 6 pi over 3. That's goes 2 pi. Then it's going to go 8 pi over 3. Then 10 pi over 3. But anyways, let's just keep the same pattern up. So this is at 3 over 2 pi is equal to 4 pi. So then theta is equal to, this is going to move it over there. So it's going to be 8 pi over 3. then r is equal to 2 plus cosine 4 pi. This equals 2. 2 plus 1 equals to 3. And again, you can see exactly why my calculus book, calculus manual, solutions manual stated all this. So you can see right here, increases to 3 at theta is equal to 8 pi over 3. So increases to 3, and then that's when 3 over 2 pi is equal to, well, 4 pi. So we get this one then, the maximum. Then we go to another minimum, do 2 more. So the next one is 3 over 2 theta is equal to 5 pi. So this would be minimum. All the odds are minimum. This goes to theta is equal to, I move it over, yeah, the 2 over is 10 pi over 3. And we get r is equal to 2 plus cosine 5 pi. This equals to 2 minus 1 equals to 1. So it goes 3, 1, and so on. And then every 2 pi over 3, or every pi for the 3 over 2 theta. This is going to be cosine 5 pi. And yeah, so that is what we get there. Let's double check all this. This equals to, yeah, so decreases to 1 at theta equals 10 pi over 3, and then completes a closed curve by going back to 3 at theta equals to 4. So this is basically 2 full curves, and now it's going to go all the way back. And we'll draw this out and show you how it goes, closes the curve. It's going to be 3 over 2 theta is equal to 6 pi. And that's because after, let's see, after, if we just go, let's see, this is a 2 pi. So because the thing is right here, we start off at 1, and then it goes to 3. Actually, it goes, I mean, start off at 3 here. And then when theta is equal to 2 pi right here, we get to 1. So we never actually, so this one right here. So this is the first loop. So here, we start off at 3. Yeah, and yeah, at 6 pi, what this is just going to be, well, 12 over 3. That's just 4. We can simplify it just because calculus book was doing that, so I'll just go 4 pi. Like that, or just 12 over 3. So every 2 pi over 3, that's the new point we're looking at, where we get new minimum or maximum. So we get r is equal to 2 plus cosine 6 pi. This equals 2. 2 minus, 2 plus 1 equals to 3. So now we finally got back to it. Yeah, so because we finally got back to 3, the next one's going to go to 1. Yeah, so we started off at 3, then we did a full loop at theta is equal to 2 pi. We got to 1, but that's not back to where we started from. And then we go another full 360 degrees or 2 pi radians, and we get back to 3. So now we're back, and then the next one's going to just go back to 1, 3, etc. So 2 full revolutions is equal to a full loop of this shape right there. And you can see that again. This is completes a closed curve by increasing to 3 at theta equals to 4 pi. And at theta equals 4 pi, we get 3 over 2 theta is equal to, well, 6 pi. So then there's a peak right there. Alright, and now we can sketch an approximate graph in the figure. Yeah, we can sketch an approximate graph as shown in the figure below. So we can draw this manually just to see what we can come up with. So I'm going to go like this. I'm going to let's get some space right here. So this is our y. Okay. Alright, so that's our y. And now this is going to be our x. Okay, this is our x, like that. Alright, here I just fixed that up. And now what I'm going to do is I'm going to just draw dashed lines to help easier. Because we know the minimum is 1 and the maximum is 3. So we should do that on every one of these axes. So I'm going to go 1, 2, and then 3. And likewise 1, 2, 3. Try to make it roughly the same. 1, 2, 3. And then 1, 2, 3. So we got like that. Now the first point is at theta is equal to 0. Theta is equal to 0, we get 3. So we just draw this right here. Alright. I don't know why it erased. Alright, here I brought it back up. I just undo erase. Anyway, so that's the first point. And now at theta is equal to 2 pi over 3. That's at, this would be at, yeah, that's actually at 120 degrees. And because again, pi is 180. So pi is 180, and then pi over 3 is going to be 60. So it's going to be, I'm going to draw these as guidelines. This is going to be 60. This is going to be 120. And then the next one is going to be, the next one's going to be, well, if it's 120, and then add another, this is 60 there, but yeah, this is 120, but then each time we're going to add 120, because we have right here 2 pi over 3, the next one is 4 pi over 3, in other words, we added a 2 pi over 3, so we add another 120, so that's 120, it's going to go all the way into, well, this is 60, then another 60 is going to be across here, so again, you can see the symmetry like that, and like, I'm just going to draw it like that. So anyways, so that's the first point. And then the second point is at theta is equal to 2 pi over 3. And then that we end up with 1. All right, so that's at the point here. So it's going to go 1 here. It's going to go across here 120 degrees. It's going to be roughly around there. What I'm going to do is we need to draw this. I'm going to draw a curve like that. So it goes, or make it a bit bigger. Just going to make it like this. So it goes like that. All right, so it goes like that. Just do a rough estimate. Now the next point is going to be at theta is equal to 4 pi over 3. All right, so 4 pi over 3, and again, that's just adding another 120 degrees, or we start with 180 plus 60 is us 240 degrees, and that's going to be over here, but it reaches a maximum at 3. So there it goes to 3 there. So now this has to go all the way across somewhere around here. So this one, draw a line like that. It's going to be somewhere around here. I'm going to draw it roughly here. So again, roughly like that, and or just draw this like that, so roughly like that. Alright, draw this a bit better, connect to it. Alright, so it goes like that, and now the next point is it goes back to 1, and it goes back to 1 at 2 pi, so it goes back to 1 at 2 pi, so it goes right here. So in other words, this is going to go like this, like that, or draw it a bit better. Let's say it doesn't get past, but anyways, it looks like that. And now the next setup here is going to go into 8 pi over 3. And to go from 8 pi of 3, it's just going to be exactly the same thing. It's going to be 120 plus 360, so that's going to be 480, I believe. So it goes all the way across here, but that goes up to at 3. This is 8 pi over 3, that goes to 3, and again, it's just the same thing. You're also adding 120 degrees. So it's going to go, but it's going to go all the way to 3 there. It's going to go somewhere around here, so it's at an angle, it's a bit lower than that. It's going to be a bit lower, so it's something like this. Anyways, so it goes there, and this goes all the way across there. I'll draw this a bit better. Okay, it goes like that. Alright, here, just fix that up. And now the next one is at 10 pi over 3. That's another 120. It goes over here, but it goes to 1 now. So 1 should be around roughly here-ish. Yeah, around this area. So now we're just going to go all the way, loop all the way across. Just a bit better. It's going to go something like this. Alright, here I just fix that up. And again, I'll draw the arrows. It goes like this. It goes down across here and goes up like that. So it goes down, up, and then this down like that. Alright, let's check the next one is, that was at 10 pi over 3. Now the next one goes all the way to 4 pi, goes to 3 now. So it's going to go all the way, loop it all the way across here now. Yeah, so it goes all the way, loop across there, and then it recycles back the same setup there. So I'll draw a point like that. Yeah, so anyways, so that is roughly the shape that we got from here. And here is a better sketch from the solution manual. I just copied and pasted it here, or took a screenshot of it. But yeah, this is just doing it manually, and here it is how it is. And you can see the exact same setup here. It goes like this, and then up and down. And this goes also like this. Yeah. Let's fix that up. Yeah, it basically goes like this, loops up, and then goes back, and so on. And it's yeah, it's slightly better. Yeah, no, it's better and has the center point actually goes over somewhere across there. But anyways, I could have just drawn this a bit more in the center there. So good enough. And now here, going further, we can determine how the curve passes over itself by investigating the maximum and minimum values for Z for t is between 0 and 4 pi. And that's because in the question we're asked, how does it go over and below it, and so on. So it says first, show that by, yeah, it says right here. Yeah, going back here, it says use the following parametric equation to sketch your curve by hand, with gaps indicating where the curve passes over itself. So the straight line would be on top, the gap would be the one underneath. Yeah, so yeah, going back down here. So we can determine how the curve passes over itself by investigating the maximum and minimum values for Z. And this is for the in 3D space. So this is a projection straight on the XY plane, but we want the actual three-dimensional projection. or the three-dimensional curve. We need to see where the highest and lowest points are for the z value. So and then maximum and minimum values for z for t is between 0 and 4 pi. That's where this goes all the way until it reloops and goes back into the same cycle. So since z is equal to sine 1.5t, z is maximized when where sine of 1.5t or 3 over 2 t is equal to 1. And again, going back to the curve, this was our curve right here. This is a projection onto it where z is 0, but here's just to double check, z equals 1.5t. And again, sine is minimum, maximum at basically at 1 and -1 is the max and min. All right. Note that well, what we have is, because we have 1.5t inside all of the sine and cosine and so on. So 1.5t, this is equals to 3 over 2t, and now this is equal to this is going to be maximized, and then now we need to find the maximum. But before we were dealing with the cosine, so this is the cosine. Now we need to do the same curve, but for sine. Because now we're dealing with the sine, and then from there we can find out what the t values is. So this is for z. This is for t is between 0 and 4 pi, except 3 over 2t is going to be up to 6 pi. So you can just multiply by 4. So by 4 pi. So 3 times 4 is 12. Divided by 2 is 6. So before we write these values, and I'm going to write this down. Recall just the cosine. I'm the sine now. So the same thing as before. I'm going to draw this a bit down more. Alright, this is going to be our... Alright, yeah, this is going to be our... I'll just put a theta, and this is going to be our sine theta now. And for sine theta, it starts off at 0, so it's always opposite of the cosine. So it starts off there, but now we need to do it all the way up to 6 pi. So 6 pi, and then put the center is going to be somewhere around here, 3 pi. I'm going to put pi's everywhere, so this is going to be, next one's going to be a pi. Actually, let's see, yeah, the next one's going to be a pi. Yeah, this is going to be pi. Well, actually, I'll fix that up. The next one, this is actually better. This is like that. And this and that. So this is 5 pi. This is pi, 2 pi. And this is going to be 4 pi, 5 pi. Fix this up. Alright, and then this one here, whenever it's pi, 2 pi, etc., it's always 0. So those are all the zeros. So we need to go somewhere in here. This is going to be the pi over 2. This is the peak there. In between those is where it's going to be. This is going to be 3 pi over 2. So just added by pi or 2 pi over 2. So 5 pi, then add that again. Because the difference between here and here is pi, which equals to 2 pi over 2. So we can just add those up. So then another one here is going to be 5 pi over 2, and then over here is going to be, well, 7 pi over 2. These are the minimum and maximum. 9 pi over 2, and then finally this one is 11 pi over 2, like that. So, and then this is going to be, the peak is going to be 1. The bottom, the minimum is going to be -1. Like that. So it's, and the peak is going to be at this part here. Minimum is going to be over here. And then peak is going to be always at these fractions. Yeah, then this one. And then this one here. And it's going to look like this. Goes up, goes down, goes up, goes down. Here, this goes up. And then goes like that. And then it keeps going. And yeah, it goes all the way back to the start. And so in other words, the maximum is going to be at, well, pi over 2. This is the maximums right here. So that's at pi over 2. I'll erase these now. So those are pi over 2, 5 pi over 2. And then we'll have 7, 5 pi over 2. We skip the 3 pi over 2, that's the minimum. Then we go to 9 pi over 2. Like that. Or, yeah, so these ones are for, basically, those are the maximums, but those are for 3 over 2 pi. So we need to get the t value, so that's basically t is equal to, solve for it. And then, so basically we cancel out all the 2's, and then multiply by 3. So it's going to be 3 pi Yeah, this one, the t's will, for this one will be 3 pi. The next one is going to be, well, this is going to, I mean, you divide by 3. No, my bad. Yeah, so divide by 3. So here, the 2's canceled, and we move this over underneath, so we're going to get a pi over 3, or 60 degrees there, and then this is going to be 5 over 3 pi, and then the next one is going to be, well, 3 divided by 3 pi divided by 3 is going to be, well, 3 pi. Yeah. All right, so we can box these ones in. So these are t values at maximum. And now I'm going to circle those just so that it's not associated with those other values. This is just a signed function. And then we're considering this one for 3 over 2 t, how it would be, and then from there just solve for t. And now the minimums. And when we look at the minimums, well, z is going to be minimized where sine of 1.5t is going to be the smallest, in other words, -1. And that's going to be at this right here. So we're going to write this as 1.5 t equals to 3 over 2t, which equals to the minimums are going to be at here 3 pi over 2. So right here, here, and here. Those are all the minimums. Let's erase these arrows. All right, let me just finish erasing those. And one more, and then so this is going to be at 3 pi over 2. 3 like that. And then the next one's going to be 7 pi over 2. Next one's going to be 11 pi over 2. And then from there we could solve for t. So t is going to equal 2, cancels all the 2's out, and then divide by 3 on every single one. So this is just going to be pi. Next one is going to be 7 over 3 pi. Next one's going to be 11 over 3 pi. So those are the minimums there. So I'll box this out. And now note that these are precisely the values for which cosine 1.5t is equal to 0. And you can see that from above here. So again, these are the pi, 7 over 3 pi, and then 11 over 3 pi. Or we'll just look at these ones right here. 3 pi over 2, 7 pi over 2, 11 pi over 2. Scroll all the way back up here. And this is at... before we even get to that, every single one of these are that. Yeah, so the minimum and max. So note that these values, I'll write here, both minimum and maximum, for which cosine 1.5 t equals 0. So if we look at the first one is pi over 2. So you look at pi over 2, and that's this one here. This is pi over 2. So that's 0. The next one's going to be 3 pi over 2. This is a 0. And we can see that here. Now let's write that. So that's pi over 2. So this one's pi over 2. The next one's 3 pi over 2. The next one is 5 pi over 2, 7 pi over 2. And then we'll go right here. This is going to be 9 pi over 2, 11 pi over 2. So I'll just write these all for completeness because it's already drawn out. It's going to be 5. And we just add 2 pi over 2 to every single one. This one right here is going to be at 7 pi over 2. And then this is going to be 9 pi over 2. 11 pi over 2. Alright, there it is. Alright, so what that means is, well, if cosine is 0, and we know that r, so r is equal to 2 plus cosine 1.5t. So we know that r, going back here, this right here, so r equals 2 plus cosine 1.5t. So in other words, we're going to have, so then that's equals to 0, so thus, I'll put a thus, r is equal to 2 plus cosine, and then I'll just put 1.5t, this equals to 2 plus 0 equals to 2. So at the minimum or maximum of the curve in the z-axis is when the distance from the origin of the polar equation, that's of the projection onto the xy plane, is when the distance is at 2. So in other words, it's somewhere around here, here, and here, and then from there we can see where is it overlapping and not. And here I quickly updated this to include these gaps right there. I mean, not the gaps. I made this so that this is more centered over there. All right, so it looks something like that. All right. So what I'm going to do is I'm going to copy. I'm going to copy this, and then we're going to use a screenshot from my calculus book. I'm going to copy this. All right. All right. So continue further. So on the graph of the projection, these 6 points appear to be at the 3 self intersections we see, and again, that's at this point, and this point. That's roughly where it is at distance r is 2. So roughly where r is equal to 2, roughly there. So those are the points, and then we could determine where the t corresponds and to which one's below and which one's above. So comparing the maximum and minimum values of z at these intersections, we can determine where the curve passes over itself, as indicated in the figure below. So what I'm going to do is I'm going to put my sketch first, and then I'm going to do a screenshot of the calculus book solution manual. So here's my sketch that I did earlier. So put this like here. So assuming that I'm going to erase these, this was just a guide. So this was just a guide. Like that. And now I'll erase this as well, what I had on the top. Erase the guides. That was the guide for the 120 degrees and 60 degrees and so on. So what we have here, and I'm going to add this eraser. There should be an eraser right here. Eraser, and I need to add it the normal eraser. This is the point eraser, and make it smaller. Okay, I don't know why it doesn't allow smaller size. All right, yeah, it should be good. So now what we have is, so I have an eraser, and so comparing the maximum minimum values of z at these intersections, we can determine where the curve passes over itself, as indicated in the figure below. So if it's somewhere around here, here, and here, what we could do is, well, we know that at this point right here, this is going to be around 5 pi over, yeah, just about pi over 2, so roughly there. So pi over 2, well, becomes pi over 3. That's a maximum. So at pi over 3, around there, which is this is 60 degrees. Yeah, remember, pi over 3 is 60 degrees. Pi over 6 is 30. And then remember, the reason is if you multiply by 3 times, you get 180 degrees or pi. So in other words, that's pi over 3. That's a maximum. So that's a maximum. So that means, and that's the first loop. So in other words, this one's a maximum, and then the other one's going to be a minimum. Well, we know it's a minimum because let's go back here. So at pi over 3, then doing adding a full 2 pi. So what I'll do is I'll go back to this pen. So if we have pi over 3. T equals pi over 3 is maximum, and then if we add a full 2 pi to it, so we have and then pi over 3 plus 2 pi, that's a 6 pi over 3, that equals to 7 pi over 3. So max, and then I'll erase this like that. This one here, this is 7 pi over 3, and go back to where it was. This is 7 pi over 3. This is a minimum. Yeah, so I don't know why it's not writing anymore. Yeah, this is a minimum. Yeah, so in other words, this is a minimum. I just wanted to illustrate at least the first point simply. All right, so this is a minimum right here. Okay, this is a minimum. So in other words, the one below it is the minimum, so we can go and use our eraser and basically erase. I'm going to erase this whole thing. Yeah, so erase the whole thing, or make it a bit closer, and erase it. I'm going to erase right here. Yeah, so actually, I'll just do eraser at one time. I don't know why it doesn't do it. Okay, there's the eraser. I'm going to erase every single point right here, and erase this one as well. Alright, so now I'm going to change this eraser. Alright, anyways, now that I've changed that, so basically this one is a fixed line, the one below it is, is the minimum. That's the maximum, is the minimum. And now if we go over here, let's take a look at when, this is at, pi. So, so t is minimized at pi. So in other words, and then at 3 pi is maximum, so that's a full 2 pi. So in other words, the one after it is it. So this one here is below, then goes above. And now this part right here this is in this quadrant, so that's going to be just below 2 pi there. So let's take a look at this part right here. So it's a maximum at 5/3 pi. So that's closer to 6 pi. So that's going to be a maximum. And if you look at the alternative, this is 11/3 pi. That's a full 2 pi around it. So this one's going to be a minimum. So at this quadrant, when it's getting closer to 2 pi, is a maximum. So it's going to be maximum. It goes above. And then on the second time around is 11 pi/3. That's going to be a minimum. So in other words, it's below. So there it is. How it looks like. This goes in and out like that. So it's epic stuff there. And all right, here going further. So yeah, here's a sketch from my calculus book solution manual, and it's exactly the same thing we have here. So it goes above, below, it goes above, and then it goes below, and then above. Above, below, above. Yeah, so above, below, above, below, above, below. And again, it's the same thing. Above, below, above, below, above, below, and so on. Keeps going on and on. There it is. Pretty cool stuff there. And it's again same thing as this one, just a bit more neater here. So and here is my calculus book solutions manual. It uses it provided these graphs as well. So we show a computer graph, a computer drawn graph of the curve from above, as well as views from the front and from the side. So this is how it looks like here. This one, yeah. So this is pretty close, but this is note that the y is on the bottom here, the x is on there. And notice that it looks very similar to ours, except there is these little inflection points. So it goes like this, and then there's an inflection. There's a big blob, and then inflection. Big blob, then inflection there. So that's pretty cool. And then there's it looks very, very similar. But then look at how the shape is. Yeah, so it has an inflection point. Yeah, so yeah, I mean, it goes like this. It goes like this, and then inflection, and then inflection. So every time there's an inflection point. Ours didn't have that much detail, because we were just trying to draw it by hand. So again, this is why computer is going to be much more accurate for these complicated graphs. And here's the front view. Looks all like this. So then from the top view, there's no way you can tell that this is going to look like that from looking at this. And side view looks like that. Looks like kind of like a fish or a missile. So the top view graph shows a more accurate representation of the projection of the trefoil knot onto the XY plane. The axes are rotated 90 degrees. Just a note here, this is X, this Y, as opposed to X and Y. All right. And yeah, so it's rotated, so 90 degrees. It should be over here. Make it upside down, yeah. All right, and note the indentations or the inflection points the graph exhibits at the points corresponding to r equals 1. So at r equals 1, so which we ignored here. So this part's right here, the closest point here. This should be an inflection point. It should be like something like that, bends over. All right, and yeah, that's r equals 1. This is r equals 1. So at these at this point right here. So that's quite fascinating stuff. Yeah, so that's like that. And corresponding to r equals 1. And finally, we graph several additional viewpoints of the trefoil knot along with 2 plots showing a tube of radius 0.2 around the curve. So here's how this looks like. You can move it around. Looks pretty cool. And now here it is with the tube, so you can see it going in and out. So it goes like that. It's pretty epic stuff here. In our case, it would start off from here, above, below, because it's just... Because in our case, our graph, the arrow was pointing to the right. Or if you look at the 2 blobs, so it's like computer's loading up. Yeah, this right here. So it looks like, so it has a direction. In this case, if you draw a triangle, it points to the right. Like that. It's just point to the right, just so we know that that's the one we were looking at. And so, yeah, again. And then there it is in 3D. You can see it going in and out and out. So pretty amazing stuff. So and here's a trefoil knot plotted in GeoGebra. So if you type it all in here, and I graph it from 0 to 6 pi, and it loops around. So it looks pretty cool. And here's a top view. There's indentation and so on. And there's from side view. Another front view, or yeah, that's front view because that is the Z. There's the X. And note that GeoGebra doesn't have a tube command, so I had to create a surface via Grok AI. Just asked it. that has a circular cross section around the trefoil knot curve. This one's a bit simpler than the other one. I did this in my earlier. I think example 7. So basically, this one, the whole I just used Grok AI to tell me what to do, and basically it has. This is our parametric equations. I don't know why it's not writing. Okay. Yeah, this is our parametric equation. Then it adds a second parameter u. So it adds 0.2 cosine u on this one here, and then 0.2 sine u. So it keeps adding on the x and y coordinates by u, where u wraps around a circle. So from 0 to 2 pi. So it somehow does that and makes a surface, and you could see it in there like this, and it looks like this. So yeah, there it is. This goes above, below, above, below. So above, below, above, below, above, below, and so on. Loops all the way around. There it is from a 3-dimensional view, and so on. And also, here's the same plot in Desmo's new graphing calculator, which has a tube automatically in. Yeah, so in Desmo, so yeah, they just created a new one, trying to compete with GeoGebra. Because I used to use Desmos for 2D, and I'll go over here, and I will use Desmos later. But anyways, so here's the graph, and here's you can play around with it, and it's pretty giant. So there's all the equations. Let's close that all up, and you can move it around. All right, and then what you could also, then you go all the way to the top, and there it is, perfect shape. Absolutely amazing. And yeah, so that's amazing stuff there. So 3D with the tube, you can see how it actually is. And if I can remove the surface, there's the curve. There's a surface right on top of it. Perfect setup there. And the surface just makes a cross-sectional area anyways around it. So another thing I wanted to show is if you add, let's say, 5 pi, and then graph it out, see how it doesn't fully loop around. So I think I didn't include, did I not press enter? Yeah, I need to press enter. 5 pi, enter. Alright, so we added 5 pi. Let's see how it cuts off. So it's still graphing it, so I don't know what's going on. It shouldn't graph it. Oh, that's T. Okay, so it's T, yeah, T goes to 4 pi. So because remember, the other one is the 1.5 T is from 6 pi. So I'm going to put 3 pi. Yeah, and yeah, there it is. So see how it doesn't fully loop around. So we need another 4 pi there. So we need 4 pi at least. Yeah, so there's full setup there, and then there's the setup there. This is the surface, and again, yeah, it takes a lot of computing power. Anyways, that's how it is. I'm going to close this, leave. And now here is the Desmos calculator. You can also do that in here. You just plug it in. Put the parametric equations. It automatically draws this. And again, this should be in 4 pi. And if you go erase to 3, there it is, cuts it off. This is 4. Yeah, so that is, should be like that. And yeah, it looks like they're not there. But yeah, some pretty epic stuff there. All right, I'm going to close. I'll just leave this open. Alright, so yeah, epic stuff there. And alright, now let's take a look at the fourth and final exercise. And note that this exercise, this exercise is from an earlier chapter on parametric equations and polar coordinates, but I had not done a video on this particular exercise during that, and I referenced it during this chapter, so I might as well go over it. And this is on the trochoid. So basically, this one asks, let P be a point at a distance d from the center of a circle of radius r, and the curve traced out by P as the circle rolls along a straight line is called a trochoid. So if you have a circle and then P is just a point on it or anywhere, and is a point at a distance d from the center of the circle. Doesn't need to be on it. Doesn't need to be at below or above it, but anywhere. And then as it rotates, the curve traced out by P as the circle rotates or rolls along a straight line is called a trochoid. Think of the motion of a spoke. Think of the motion of a point on a spoke of a bicycle wheel. So if you have a point like here, and if you're tracing it around, so as you're spinning around like this, but as you're moving as well, you're gonna have a shape that goes up like this, and so on. And so again, but it goes backwards as well. So it's gonna look. I think it's gonna look something like this. If you're tracing this always. This is gonna go. It's gonna go down, and then it should go back up. This is going backwards, and so on. It's something like that. But anyways, the cycloid is a special case of a trochoid with d equals r. So if you have a point right here, distance from here, if this is below, this is inside the circle, the shape's gonna look something like this. If the shape is if the point is on the circle, it's gonna be a trochoid, basically like this. Like this curve and point, sharp curves. But if it's outside of the point that you're circling around is outside of the circle, it's gonna have a loop like that. It's gonna have a loop. Yeah. So the trochoid is formed by tracing any point inside, on, hence the cycloid, or outside a circle as it rolls. And I will just illustrate this right here first. So here is this is a cycloid. See how the cycloid is? It hits like that, and it's on it. And now here is the next one. This is a proloid trochoid. A prolate trochoid basically means the point that's curving is outside of the circle. And then last one, this is a curtate trochoid. This is the point is inside the circle, so it never touches. So it doesn't have sharp edges or a loop. It's a pretty cool stuff there. All right, so that's what we have here. So now we're stated using the same parameter as for the cycloid, and assuming the line is the x-axis and theta equals 0 when p is at one of its lowest points. Show that parametric equations of the trochoid are x equals 2 r theta minus d sine theta and y equals r minus d cosine theta, and sketch a trochoid for cases d is less than r and d is greater than r. Alright, and yeah, so let's take a look at the solution. So recall from my earlier video on the cycloid, I showed like this, or here's a screenshot. Cycloid is like this. And again, I covered this earlier, but this is an exercise. I'm going to put this all in one video here. So this rolls like that, becomes this shape like that, and so on. And then I used basically you can draw it using trigonometry to find the x, y coordinates using the arc length and so on, and then determine this value is r theta. This distance r theta is just the arc length, and it never slips, so it's always going to be the same distance. And it rolls around, and then I showed that x equals to r times theta minus sine theta, and then y equals to r times 1 minus cosine theta, and theta is all real numbers, like that. Just goes anywhere, negative infinity, plus infinity. So the first two diagrams of a curtate trochoid, d is less than r, depicts the case where pi is less than theta, which is less than 3 pi over 2, and d is less than r. And I'll unpack this soon. Basically, and also, I mean, the first two diagrams below, so I will draw these out. So what we're going to have is we're going to do a curtate trochoid, not a prolate. So basically, if we have the x and y like this set up here, so this is, and we'll start the origin like this. This is 0. This is the x, and now this is the y. So let's say we have a circle. So I'm going to draw a circle like this. I'm going to draw it over here. Alright, and then the lowest point is going to be here. And actually, I want to see where the point is. It's going to look something like this. So here's the center C. Center C. And then this distance is r. And it never stops rolling. So I'm going to draw the point where it depicts the case where theta, I'll put this right here. Yeah, I'll make a space like that. Where theta is between, yeah, I'll just keep it like that, it's alright. It should be straightforward. Yeah, actually, I'll erase this. This is curtate, we already covered that. Okay, so a trochoid depicts the case where theta is, and here I quickly just fix up the sentence. So the first two diagrams below depict a curtate trochoid. That's when d is less than r. 4, where theta is between pi and 3 pi over 2. So in other words, we're gonna take the angle starts from the lowest point. So it's gonna start from here, and I'm gonna draw a this is the curve. This is the point P right here. This is distance d. This is the point so far. And it's going to look something like this, and it goes up like that, and the lowest point, the highest point is going to be somewhere here, so it's going to go something like this, and then it goes down. The lowest point is going to be somewhere around here, so that's the lowest point. This is the highest point somewhere here. I'll draw it over across there. So we just got to look at like how it looks like. I'll draw this better, and this is something like this, like that. And it looks like that, yeah, and it's curling, and it goes back up like that. So that's a curtate one, and if this is pi, up to here is pi. This is theta. So there's our angle theta, like that, and there's our radius r. Oops. Okay, and here I quickly fix up the circle. I just added a perfect circle using the OneNote little circle insert thingy. And this is the point P right here. So this is the point P, like that. So that's the point P, and this is between so this point right here is theta is greater than pi, because it's pi is 180 degrees, and it's going to be below 3 pi over 2, which is across here. That's 270. All right, and now this distance from here to here, this is just, this distance is going to be r theta. Yeah, this is r theta, and again, this is because there's no slipping, and that's just the arc length. So no slipping. as circle rotates. And it's always in contact. Circle rotates. And if it's always in contact, that means, yeah, it's the entire time it was in contact, that's the full length it went to. And in other words, this full length across, all the way across here. So that this full length all the way across is always in contact. And that's just using definition of radiance. That's just r theta. Yeah, that's basically arc length. And again, that's just arc length. All right, and that's the first diagram. But then the first two below, I'm going to draw another diagram right here. All right, so here I'm going to just paste a circle right here. So there's a perfect circle. And I'm going to zoom into that. Okay, so we have this set up like this. Okay, so we have that. And now what I'm going to do is draw the R. So R, there's the center. There's the R. So that's R. This is the C. And now we're going to draw this all the way to P. So there's a point P. And I'm going to draw a point Q like this. There's a point Q. Okay, let's fix this up. This point Q. And now this is going to be, so if this is theta, yeah, I'll just put it better like this. So this angle, like here, this is theta, this is D, this distance is D, all the way from there to there. And here, quickly pause the video, just made this triangle a bit bigger. So there's our Q, like that. And yeah, I'll fix this up like this. This is our Q. This is our center. I'll put the R on this side, so it's not in the way. There's our D. I'm just going to put the theta. I'm going to put an angle right here. This angle, this one here, is going to be equal to, I'll just move it actually out. Yeah, I'll put this, yeah, I'll put it right here. This angle is going to be theta minus pi, because remember, this is pi, so this is the full angle. And then up to here is pi. Yeah, so that's full angle. And then up to, from here, just a straight line, just a pi there. And now we have to, well, what we could do is we can determine the points here from C to Q. This distance right here, this is just going to be using Pythagoras. So if we just using, trigonometry. So cosine of theta minus pi is just equal to, well, adjacent equals adjacent over D. Yeah, so adjacent over D, and D is just the distance to the point P. So that's D. So move this D over to the other side. So in other words, we get a D times by cosine the pi minus theta minus pi. All right, yeah. So that's pretty straightforward. And now this one right here, this is just going to be, well, sine. Right, and also this is pretty straightforward. I'm just going to erase this. So we know it's, yeah, cosine is basically, trigonometry is always adjacent over hypotenuse. And now this one is opposite of our hypotenuse. So it's going to be, this case is going to be, yeah, this is the opposite one. So this is going to be sine instead of cosine. So it's going to be D sine theta minus pi. Like that. All right. Again, this is, yeah, D times it by, just because it looks like it's a derivative. But anyways, that's what we have. All right, and yeah, now we're going further. So as for the cycloid, the center C of the circle has coordinates R, theta, R. So again, that's R, theta, then R. Since there is no slipping as the circle rotates, and i.e. the distance traveled is just the arc length that has rolled on the ground. And now the coordinates of Q, yeah, the coordinates of Q and of Q and P are thus, so I'll just write down for completeness C as well. So C is equal to, the coordinates are R theta, the arc length of the circle that it's rolled, R, and that's just the height of that circle there, or the radius. And now the Q is equal to, well, Q is right here. So Q is, the X1 is just R theta. Yeah, that's just R theta, and then the Q is going to be above here, so we need to add, for the Y component, R plus D cosine theta minus pi. So this is going to be R theta. Okay, it's not writing. Alright, there it is. This is going to be R theta, and then it's going to be R plus d cosine theta minus pi, like that. And then we need to add one more bracket for around it. All right, like that. And now the next one is this is p now. The coordinates are, so p is going to be an interesting one. This is going to be, well, r theta, and now p we need to add another d times sine theta minus pi. So that's going to be on the x axis. So this is going to be r plus d sine theta minus pi, like that. And then the height is going to be, well, the height's going to be r plus d cosine theta minus pi. So it's the same as q. So this is going to be r plus d cosine theta minus pi, like that. And put another bracket around it. And now we can simplify this by using the trigonometric identities, because we know we want to simplify, get rid of this this theta minus pi. Just keep it a theta by itself. So recall. So I'll do a block like this. So recall that if we have just a triangle like this, and we can see the xy, and I'm just going to say, let's say we had a triangle like this. Let's try this a bit, yeah, farther. Okay, so there's let's say we have a theta like this, and then this is our b. Let's say we have adjacent b, opposite adjacent a, opposite b, hypotenuse c. Then what we have is, well, we know that cosine theta is equal to a over c, adjacent over hypotenuse. Sine theta is equal to opposite over hypotenuse. And now, if we were to draw a perfectly in line like that, triangle like that, and basically go backwards like this. So now this is, we just mirror it exactly. So this is going to be like that. This is theta. And this is going to be negative b. This is negative a. Like that. And then the c is always, the distance is always positive. Like that. And then this distance from here to here. So basically what we're doing is subtracting by 180 degrees. This is just pi. Pi like that. And this doesn't matter. This doesn't matter if we plus or minus pi. So if we plus pi or minus pi, we're also going to get over here. So in other words, right here, what we end up having is cosine. Yeah, so we're going to subtract a pi. So I'll just put a minus like that. So this is going to be, we're subtracting a pi or plus. It doesn't matter. So cosine of theta minus pi, this equals to, well, now we're going to be dealing with negative adjacent over c. So this equals to negative adjacent over c. And that just equals to, well, negative cosine theta. And likewise, for the sine is going to be theta minus pi equals to opposite over hypotenuse. Now it's going to be negative b over c. This equals to negative sine theta, like that. All right, so now that we've done this, simplified it, so thus we can simplify our setup. So thus, and let's write everything back down. So again, the center is still going to be r theta, r, and now we're going to have the q is going to equal to r theta, and this is going to be r plus or minus. So it's going to be r minus d cosine theta, because now we replace this right here with negative cosine theta, and the other one is going to be negative sine theta. So we replace that. So that's going to be, let's write this all out. All right, so this is going to be r minus d sine, cosine theta. All right, and then the p, this one's going to equal to, well, it's going to be r theta plus. Now we move over to this, to the d sine, but now we're going to subtract d sine theta, and again you could see that over here. So r theta plus d sine theta minus pi. Now this becomes just negative d sine theta. And then it's going to be the same. The y component is going to be the same as the q. R plus d cosine theta minus pi, but in other words, it's going to be negative d cosine theta. So in other words, it's going to be r minus d cosine theta. All right, and now that we have all these points, and the only ones we're interested in is just the point P. We don't care what the point the point Q and C aren't what the trochoid is defined as. It's just the point P that's rotating around. If it's just a point Q, that would be an interesting one. It will never go. Actually, yeah. What would the point Q go to? It's always over here. It actually would be somewhat similar. If it goes all the way down here, where would Q be? Anyway, that's another topic for another day. But anyways, we're only focused on the point point P. So the x and y components of it are the equations. That's just the parametric equations of a trochoid. So in other words, we're interested in this. This is our x. This is our y of a trochoid. So our trochoid is going to be now the parametric equations x equals to r theta minus d sine theta, and y, I'll put it like this, I'll actually put it over here, y equals to r minus d cosine theta. So there's our trochoid. Like that. Alright, going further, when d is equal to r, these parametric equations of a trochoid agree with those of a cycloid. Basically, when d is equal to r, so when d equals to r, so it's on the actual edge of the circle, so on the circle itself, that just becomes a cycloid, and we can see that. So for d equals to r, what we end up having is x is equal to r theta minus d is going to be r, so that's going to be r sine theta. Then y equals to y equals to r minus r cosine theta. In other words, this equals to r. Factor it out. 1 minus cosine theta. And this is just a cycloid. And then this one is equal to, well, take out the r theta minus sine theta. That is a cycloid. And we can scroll all the way up, and to see that from the beginning right here, this is a cycloid, and x equals to r times by theta minus sine theta, and then y is equal to r, and then times by 1 minus cosine theta. So yes, again, exact same setup we did here. This one started from here. I should have done something like that, but Kakel's book was just doing some other method like this. But anyways, it's probably the same thing. And that's probably easier just because you're sticking on this point there. But anyways, I forgot what I did exactly there, but it's pretty interesting nonetheless. And so we got all these covered. Now we're going to do some graphs. This is from my Kakel's book, Solutions Manual. So a prolate trochoid where d is greater than r is graphed below. And you can see how it looks like right here. And it loops around like that and so on. Thus d is greater than r like that. And here are graphs of the trochoid using the Desmos 2D graphing calculator. So as opposed to the 3D graphing calculator or GeoGebra. I like Desmos 2D. I was using this before, but it didn't have a 3D until now, but it's still not as powerful as GeoGebra. So here's the graphs of the trochoid using Desmos 2D graphing calculator. So you can just plug in RT minus D times sine T. Yeah, because you can't put theta in there. So this is theta. So R theta minus D sine T, or just think of it as theta. And then, this is the X. That's Y R minus D cosine T, like that. And you can see it will graph it out like this, and you could vary the values, and then you can see this is a let's see what this was called. This is a prolate. The other one is called a curate, or was it called curtate? Yeah, here I quickly went to the Wikipedia. So it's a curtate. So there's this is wrong as well. This is a T there. So a curtate trochoid is like that. Let's see if I wrote it anywhere else. But yeah, I don't think I wrote it anywhere else. Anyways, so a curtate trochoid is like that. It's pretty epic stuff. Yeah, all right. Let's go back here. Yeah, so so here's the graph, and you can see this. So when D is above it, you're gonna get this curtate setup like that. And I also draw the circle there just so we have the same setup there. And this is r cosine, and then where r, if we can adjust to r. Yes, you can see it like that, and it goes around like that. And now let's do d equals to 1.3. So now we have a cycloid. Yeah, cycloid should be 1. Yeah, so now we have cycloid. This is almost a cycloid. Now it's a cycloid. Now if we go below, we get a curtate. And then this is a cycloid, and then a prolate trochoid. And there's the R. I put this here just for reference. So if you have a super small one, but then a D is super big, you can make it super small. Make it super big, it looks like that. It's pretty epic stuff. You can make crazy shapes just by circles. So, and here's an amazing trochoid animator someone made on Desmo. So here's a link to that, and it shows you rotating. They did a bunch of other stuff on here in animation. You can click it and figure that out on your own. I'm just going to click this right here. It's pretty epic stuff someone made. So here is like that. And this is where D is greater than R. But you can adjust it. And then you can go over here and press play. I think this is it. No, that's not it. Where's the button? This is the play button. Yeah, it's rotating now. Let's go back to the beginning. Yeah, so now go and play it. Yeah, so absolutely amazing stuff. And this is from a calculator. Hold in, you can move around. So whoever made this, bravo. Absolutely amazing, amazing stuff there. And there's all the links. There's all the screenshots of the stuff here. So they added a second parameter there, I think. Yeah, RA. They added an A there so that you can adjust it. So basically you have your setup there, but now you're multiplying it by a variable that can adjust and play around and so on. So they have an A there in every single variable has an A except the R there. So there's this one here, A2. So anyways, you can play around with that and figure out exactly how they did that. But yeah, epic stuff there. Anyways, and then yeah, there's prolate trochoid. Anyways, that's all for today. Hopefully you enjoyed this epic long video. I think it's 4 or 5 hours or something like that. But anyways, epic stuff here. And yeah, I hopefully enjoyed. And so I'm going to scroll all the way back up. And again, all these notes and the links to all the playlists and sections playlists and so on, and the PDFs and the notes in the Hive blockchain on in article format, all in the links in the description below and so on. But most of the other links is gonna be inside the actual Hive notes, and check those out. And also again, PDF notes, I'll print these out. Save these as PDF and save them as well. And again, it's some epic electromagnetic stuff there. Anyways, that is all for today. I'm going to scroll all the way back up. Again, this is one of my longer videos. I'll try to power through a lot of these videos more often. Yeah, just be more focused on this, especially because it's math easy. Is a lot of people say it's one of the best explaining of complex stuff like here in a way that you can actually save and download and study, and then basically almost replace your actual schooling. Anyways, that is all for today. Thanks for watching, and yeah, stay tuned for another. And again, it's still going up. I'm going to scroll all the way back up. Let's see how long it takes. Scroll back up, and let's see. There it is. Yeah. So, and stay tuned for the rest of the series. It's going to be a pretty epic stuff on this one. We're going to go over derivatives, arc length, Kepler's laws, and so on. Anyways, that's all for today. Thanks for watching, and stay tuned for another math easy solution.